Please subscribe to support the channel. What if humans are not the first advanced civilization on Earth? That single question is enough to stop us in our tracks and make us rethink everything we assume about history, progress, and even our place in the universe. We look at the ruins of ancient civilizations like Mesopotamia, Egypt, or the Maya and marvel at how far we've come. But those civilizations are only thousands of years old, a mere flicker compared to Earth's unimaginably long timeline. Now ask yourself, is it possible that another civilization, one that was industrial, technological, and intelligent in ways we can barely imagine, existed millions of years before us? If such a civilization once flourished, would we even know about it today? Or has time, geology, and natural forces buried their entire legacy so deeply that it has been wiped clean from the record? This question isn't just a curiosity, it's a mystery that digs into the very fabric of Earth's history, and it invites us to consider the possibility that humanity might not be the first to rise on this planet, but simply the most recent. The mystery grows deeper when we begin to consider that this question has actually been studied in a scientific context, not just in myths or science fiction stories. In 2018, two researchers, astrophysicist Adam Frank and NASA climate scientist Gavin Schmidt, posed what is now known as the Silurian Hypothesis. This is not a claim that another civilization definitely existed before us, but rather a carefully constructed thought experiment. The idea is simple in its framing but enormous in its implications. If an advanced technological civilization had arisen on Earth millions of years ago, long before humans appeared, would we be able to detect it in the present day? And if so, what kind of evidence would survive the relentless erosion of time? By putting this idea forward, Frank and Schmidt were not indulging in fantasy but engaging in a test of logic and science. They asked, what traces does human industry leave behind today? And how would those traces appear to geologists millions of years in the future? If we can determine what is detectable, then we can also turn that lens backwards, searching through the Earth's strata for similar markers that might suggest some unknown civilization in the distant past. In other words, the hypothesis is less about resurrecting hidden histories and more about improving our ability to recognize the fingerprints of industrial activity across geological timescales. The name Silurian Hypothesis might sound whimsical, but it hides a rigorous intellectual exercise. In naming their idea after the Silurians from Doctor Who, Frank and Schmidt immediately caught the public's imagination. The Silurians in the television series were portrayed as reptilian humanoids who developed a sophisticated culture millions of years before humans evolved, retreating underground during catastrophic changes and later resurfacing. By borrowing the name, the scientists created a cultural bridge that invites curiosity, but they quickly clarified that their work is grounded in scientific reasoning, not the mythology of television. It was never about claiming that lizard people once ran factories on prehistoric Earth, but instead about training ourselves to ask sharper questions about evidence, time, and the survival of technological markers. What makes the Silurian Hypothesis fascinating is that it confronts us with the scale of deep time. Our species has been around for roughly 300,000 years, and our industrial age, our factories, our cars, our digital infrastructure, is less than 2 centuries old. Against the 4.5 billion year history of the Earth, we are less than a blink, less than a heartbeat. If another civilization had emerged 50 million years ago and had burned brightly for even 50,000 years, a duration much longer than our own industrial span so far, it would still be a mere speck in geological. After their fall, nature would have had tens of millions of years to erase their presence, just as it erases mountains, oceans, and continents over time. That realization is both humbling and unsettling. Frank and Schmidt also framed their hypothesis within the broader field of astrobiology. If we want to search for intelligent life on other planets, we must understand what signs such a civilization might leave behind in the long run. For example, when astronomers study exoplanets, they often consider atmospheric composition, looking for traces of oxygen, methane, or carbon dioxide in ways that could suggest biological or even industrial activity. But here's the problem: if industrial civilizations rise and fall quickly in cosmic terms, their window of detectability might be tiny. If Earth hosted an earlier civilization millions of years ago, and we can't even find its traces today, what hope do we have of finding the remains of alien civilizations light years away? The Silurian Hypothesis thus becomes a kind of mirror, forcing us to confront both the fragility of human achievement and the difficulty of detecting intelligence in the cosmos. The thought experiment pushes us into uncomfortable but fascinating territory. We like to think our skyscrapers, satellites, and digital archives are permanent monuments to our intelligence. Yet the Silurian hypothesis challenges us to imagine how quickly those monuments would crumble under the forces of geology. Entire cities could vanish under layers of sediment, oceans could rise and fall, continents could drift and collide, and in a matter of a few million years, the recognizable footprint of human civilization might be reduced to subtle chemical traces embedded in rock. If this is true for us, then it must also be true for any civilization that may have come before. One of the most intriguing aspects of this hypothesis is that it doesn't require us to believe in conspiracy theories or hidden artifacts. Instead, it works entirely within the framework of mainstream science. It acknowledges the rarity of fossilization, the destructive power of plate tectonics, the erosion of landscapes, and the recycling of Earth's crust. It acknowledges that human technology is extraordinarily recent compared to Earth's history and asks us to measure our assumptions against that backdrop. Could it be that we simply wouldn't notice if someone else had already walked this path long ago? The Silurian hypothesis ultimately invites us to look at ourselves with new eyes. If we vanish tomorrow, what would future geologists find 10 million, 50 million, or 100 million years from now? Would they uncover the remnants of plastics, synthetic compounds, or unusual isotopic ratios in the rock? Would they notice a sudden spike in carbon levels corresponding to our burning of fossil fuels? Would they see disruptions in the fossil record corresponding to species lost during the Anthropocene extinction? In asking these questions, Frank and Schmidt created a thought experiment that is not about proving the existence of predecessors but about holding up a mirror to humanity itself. We are, in essence, running a test on our own legacy. What if there really was another technological civilization? Would they too have burned through fossil fuels, altered their planet's climate, and left chemical scars in the rocks? Or would their rise and fall have been so fleeting, so delicate, that even the rocks forgot them? These questions remain open, but the hypothesis ensures they can be asked scientifically, without needing to resort to legends or myths. It is not about proving Atlantis. It is about teaching us how fragile evidence can be in the vast span of time. The term itself, Silurian hypothesis, has an unusual story, and understanding where it comes from adds a layer of intrigue to the whole discussion. Unlike many scientific theories that carry austere, clinical titles, this one is rooted in a playful borrowing from popular culture. The word Silurian was not chosen because of its geological accuracy, nor because it describes some previously unknown scientific principle, but because it captures imagination. It comes straight out of Doctor Who, the long-running British science fiction series that has been weaving tales of time travel and alien encounters since the 1960s. In the show, the Silurians were a race of intelligent reptilian humanoids who supposedly ruled Earth long before humans ever evolved. According to the story, these beings were technologically advanced, possessing cities, machines, and scientific knowledge. But when they foresaw catastrophic changes to the planet, they retreated underground into a kind of suspended animation, waiting for the surface to become habitable again. Millions of years later, they awaken to discover that humanity has taken their place on the surface. This fictional narrative is, of course, entirely a product of storytelling, not scientific evidence. And yet, Adam Frank and Gavin Schmidt, the two researchers who coined the Silurian hypothesis, deliberately chose this name. Why? Because it draws attention. It sparks curiosity. It provides a cultural touchstone that makes people lean in and listen. In a world where scientific papers often bear titles so technical they can seem impenetrable, here was a phrase that bridged entertainment and inquiry. It makes a reader wonder, wait, did scientists really just name a serious hypothesis after reptilian creatures from a TV show? The answer is yes, but with a purpose. This purpose is worth considering carefully. By borrowing from Doctor Who, Frank and Schmidt were not saying, we believe lizard people built cities before us. They were saying, imagine the possibility, however unlikely, that another civilization once existed here, and let's test scientifically how we would recognize such a civilization if it did. The name was chosen to highlight the strangeness of the idea while also keeping the discussion grounded in scientific rigor. It's a way of signaling, we know this sounds extraordinary, but we're treating it as a thought experiment, not a conspiracy theory. In other words, The name works as a reminder to both scientists and the public that imagination can fuel inquiry without undermining seriousness. Interestingly, the name carries another layer of resonance. In geology, there really is something called the Silurian period. This was an era that took place around 443 to 419 million years ago, long before dinosaurs, long before mammals, long before anything resembling human beings. During this time, the Earth was dominated by primitive fish in the oceans, coral reefs were beginning to flourish, and plants had just begun to colonize the land. Early terrestrial ecosystems were just forming. To speak of a civilization existing in the actual Silurian period is, of course, absurd from what we know. Complex animals had barely taken root. But the coincidence of names creates an almost poetic layering. The Silurian period represents one of the ancient deep chapters of Earth's history, while the fictional Silurians represent an imagined intelligent species that might have thrived in such distant times. By choosing a name that straddles both science fiction and science fact, the hypothesis immediately achieves a sense of depth. It anchors itself in the real immensity of geological history while also using pop culture to invite broader audiences into the conversation. For many people, the first encounter with this hypothesis doesn't come from reading an academic journal, but from stumbling upon the phrase Silurian Hypothesis online, and then realizing it has roots in Doctor Who. That moment of recognition, I know what a Silurian is, becomes a gateway into learning about geological records, industrial markers, isotopic anomalies, and all the other scientific details that make the hypothesis valuable. There's also something deeply symbolic about scientists borrowing from fiction. Science fiction has long been a sandbox for exploring ideas that eventually find their way into real scientific discourse. Think of Jules Verne imagining submarines and space travel before they were possible, or Arthur C. Clarke envisioning geostationary satellites decades before they became reality. By taking a cue from Doctor Who, Frank and Schmidt subtly acknowledged that even wild imagination can provide a framework for serious scientific reflection. After all, the question they were asking, whether traces of a long-lost civilization could be hidden in Earth's rocks, sounds like science fiction, but when broken down into data and testable hypotheses, it becomes an exercise in geology, chemistry, and logic. The choice of name also disarms potential criticism. Had they called it the prehistoric civilization hypothesis or the industrial predecessor hypothesis, it might have invited misunderstanding, with some readers assuming the scientists were secretly endorsing fringe claims about Atlantis or hidden continents. But by using a deliberately fictional name, they made it clear from the start, this is a thought experiment, not a claim. It separates their work from pseudoscience, while still keeping it engaging. In a way, it's a reminder that science thrives on curiosity, and that it can ask wild-sounding questions without crossing into ungrounded speculation. So while the Silurian hypothesis does not argue for the existence of reptilian overlords or secret buried cities, the origin of its name reflects something important, the merging of imagination and scientific discipline. The title acknowledges that science can be playful without losing seriousness. It tells us that even when confronting ideas that stretch beyond the ordinary, it is possible to hold both curiosity and skepticism in balance. And perhaps most importantly, it teaches us that science doesn't exist in a vacuum. It is part of culture, and sometimes the language of stories can help unlock deeper engagement with questions that matter. When you hear the name Silurian Hypothesis, you might think first of alien lizards or distant time periods. But behind the name is a profound challenge, to think of Earth not just as the cradle of our species, but as a planet whose vast history may contain chapters erased by time. The name is a doorway, a symbol, and a reminder that even the most serious questions can begin with a spark of imagination. When we begin to seriously ask whether another civilization could have existed before us, we can't avoid confronting one of the most staggering realities of all, the scale of time itself. Time on the human scale is easy to grasp. We count in years, decades, and centuries. We can look back to the last 100 years and see immense change, from horse-drawn carriages to space stations orbiting Earth. We can push further back to 1,000 years ago, where medieval castles and kingdoms ruled the land, or to 10,000 years ago, when agriculture was just beginning to take root and the first permanent settlements were forming. This span feels vast to us because it's the full length of human memory, the limits of our written records, and the range within which we build our myths and histories. But once we set this against the true age of the Earth, we realize that everything we know, everything we've done, is just the briefest flicker in an almost endless expanse of time. Let's put the numbers in perspective. Modern humans, Homo sapiens, have existed for about 300,000 years. Our species itself is just a newcomer on the evolutionary stage. Civilizations, meaning organized societies with agriculture, cities, and writing, only began about 10,000 years ago. That's when humans transitioned from nomadic hunter-gatherers to farmers and builders of towns. The Industrial Revolution, which gave us machines, factories, and fossil fuel consumption on a massive scale, began less than 200 years ago. Our digital age, with its satellites, internet, and global connectivity, is less than 50 years old. When you really look at it this way, the entirety of human history, from the first sparks of culture to the present moment, fits into an astonishingly short span of time. Now, compare that to Earth's history. Earth is 4.5 billion years old. That number is so large it's almost meaningless when we first hear it, because our minds are not designed to process billions of anything, much less years. One way scientists often help us grasp this is by compressing Earth's entire history into a single calendar year, a metaphor sometimes called the cosmic calendar. Imagine January 1st is the birth of the Earth, and December 31st at midnight is today. In this metaphor, the first simple life forms appear in the oceans around March. Complex multicellular life doesn't show up until November. Dinosaurs dominate the Earth around mid-December, and they go extinct on December 26th. Humans, modern humans like us, don't appear until just before 11:30 p.m. on December 31st. All of recorded history, from the pyramids to the moon landing, would fit into the last few seconds before the clock strikes midnight. That is how small we are on the timeline of our own planet. And if we are so brief, if our entire industrial story is less than the length of a breath compared to the planet's age, then there is no reason to dismiss the possibility that another such civilization could have existed millions, even tens of millions of years ago, during one of those many long-forgotten months of Earth's calendar. Imagine how much space there is in that year-long calendar for other stories, other rises and falls, other experiments in intelligence and industry that might have occurred and vanished long before we arrived. To highlight just how much time has passed, consider the dinosaurs. They appeared around 230 million years ago and dominated the planet until about 65 million years ago. That means they ruled for over 160 million years. By contrast, humans have only been around for a few 100,000 years, and we've only built industrial civilization for a couple of centuries. If another species had achieved intelligence during the age of dinosaurs, they could have built civilizations, watched them fall, and then vanished completely, leaving us none the wiser. Their entire existence could have been swallowed by the immensity of time. Even looking back to other points in history reveals enormous blank spaces where intelligence could, in theory, have emerged. For example, between the extinction of the dinosaurs and the rise of humans, there was a gap of 60 million years filled with mammals diversifying and ecosystems evolving. That's 600 times longer than the entire history of civilization. Or think of the period between the Cambrian explosion, when complex life first flourished around 540 million years ago, and the rise of the dinosaurs. Hundreds of millions of years passed in that interval alone. Within these staggering expanses, it's not absurd to wonder, could something have happened that we simply cannot see anymore? And here lies the crux of the matter. The longer the timescale, the harder it becomes to preserve evidence. Geological processes are relentless. Rocks erode, mountains rise and crumble, continents drift across the globe, oceans open and close, and the crust of the Earth is recycled through plate tectonics. When we look back tens of millions of years, much of the surface of the Earth has been reshaped or destroyed. The possibility of finding a fossil is already rare. Most creatures that lived left no trace at all. The possibility of finding cities or technologies is exponentially rarer. In fact, if humanity disappeared tomorrow, even our most monumental creations, our tallest skyscrapers, our largest dams, our sprawling cities, would erode, collapse, and vanish within a few million years, leaving behind only the most subtle chemical and mineral clues. This is why the scale of time is so important to the Silurian hypothesis. When you realize how short our existence is compared to Earth's full history, you begin to see just how much room there is for lost chapters. Our arrogance sometimes convinces us that intelligence is unique, that civilization is a singular event, but the Earth's 4.5 billion years remind us that there have been countless opportunities for something else to rise and fall long before we arrived. If humanity can appear in the last seconds of December 31st, why couldn't another intelligence have appeared in June, or October, or even earlier in that vast cosmic year? So when scientists propose the Silurian Hypothesis, they are not saying, "We believe there was a civilization millions of years ago." What they are really saying is, look at the vastness of time, and then realize how little of it we occupy. Look at how quickly evidence can vanish, and then ask, if something else had happened, would we even know? This isn't an invitation to rewrite history with myths and legends. It's a reminder of how fragile knowledge is when weighed against the immensity of geological time. It is humbling to realize that for every story we think we know about Earth, there may be 100 more erased by the simple, inexorable passage of time. When we start to measure ourselves against the immensity of geological time, one of the most unsettling realizations is just how fragile the evidence of our existence really is. We like to think of our cities, our monuments, our technology, as permanent, great testaments to human ingenuity that will stand for ages. We point to the pyramids of Egypt and marvel that they have survived for a few thousand years, or the Roman Colosseum, or the Great Wall of China, and we assume that perhaps future beings millions of years from now might stumble upon our skyscrapers or our satellites and know we were here. But the truth is far more sobering. Almost everything we build, everything we leave behind, is temporary on the timescale of millions of years. The world erases itself, over and over, until almost nothing remains of the civilizations that once stood upon it. Think first about our cities. A modern metropolis like New York, Tokyo, or Dubai might feel indestructible. But remove humans from the equation and nature would reclaim these places far faster than we expect. Within decades, vegetation would crack concrete, water would flood basements, and steel would begin to corrode. Within a few centuries, buildings would collapse, bridges would crumble, and forests would return. In a few thousand years, only the faintest ruins might still be visible above the ground, and even those would be collapsing under layers of soil and vegetation. Fast forward 1,000,000 years, and the surface of the Earth where those cities once stood would have changed so dramatically, through erosion, sedimentation, glaciation, or even submersion beneath rising seas, that almost nothing recognizable would be left. Now extend that thought further. Over tens of millions of years, the relentless processes of geology, plate tectonics, volcanic activity, erosion, and the advance and retreat of ice ages, would erase even those traces. Entire continents drift, collide, and subduct back into the mantle, recycling the very crust on which we build our world. Vast mountain ranges rise and then wear away to flat plains. Oceans expand and contract, laying down layers of sediment that bury and compress whatever lies beneath. The surface of Earth is in constant motion, and the deeper we go into time, the less chance there is that anything built by humans, or by any civilization, would survive in recognizable form. Archaeologists already face this problem, on a much smaller scale. Even when looking for human settlements just a few thousand years old, evidence is often fragmentary. Wooden structures rot, clay crumbles, metal corrodes, and only stone or ceramics tend to endure. Even then, they are often buried and broken, and require painstaking excavation to piece together. If we struggle to find traces of villages from 10,000 years ago, what hope would we have of finding a city from 10 million years ago, if such a city had ever existed? The probability is vanishingly small. Consider also how rare fossilization itself is. Most living things leave no trace in the fossil record. For an organism to fossilize, it must die in just the right conditions. Buried quickly, shielded from scavengers, protected from oxygen and decay. Then, over millions of years, minerals must replace its tissues and preserve its form. Out of the countless billions of animals that have ever lived, only a tiny fraction have become fossils. If this is true for life itself, how much rarer would it be for the remains of buildings, tools, or machines to fossilize in ways that could be recognized millions of years later? A skyscraper collapsing into rubble is not likely to become a fossil. It will simply erode into dust and sediment, indistinguishable from the rocks around it. Even the materials we think of as durable, concrete, steel, glass, do not last forever. Concrete weathers and crumbles, glass is brittle and shatters, metals corrode and oxidize. Plastics, for all their stubborn persistence in our oceans and landfills today, would also break down eventually under the assault of sunlight, heat, microbes, and time. On a million-year scale, the idea of plastics drifting intact through sediments is unlikely. They might leave behind chemical residues, but not recognizable artifacts. The Eiffel Tower, the Empire State Building, the Burj Khalifa, structures we think of as permanent landmarks, would eventually vanish completely, ground down to invisible fragments in the geological churn. The most likely traces of us to survive into the deep future are not the visible forms of our cities, but the invisible chemical scars of our industry. Our burning of fossil fuels, for instance, is altering the ratio of carbon isotopes in the atmosphere. This change is being locked into sediments and rocks, creating a kind of signature in Earth's geological record. Future scientists, millions of years from now, could in theory detect these anomalies and recognize that something unusual happened during this time. Similarly, the widespread presence of synthetic compounds, plastics, pesticides, industrial chemicals, might leave faint chemical residues. But to the naked eye, to the casual discoverer, there would be no visible ruins of civilization, no broken skyscrapers jutting from rock, no rusted cars buried in stone. Just subtle anomalies buried in layers of sediment, waiting for someone with the right tools and the right knowledge to notice. And this is what makes the Silurian hypothesis so haunting. If another civilization had existed millions of years ago, their evidence might not look like ruins at all. It might not be recognizable buildings or machines, but faint chemical fingerprints, disrupted climate patterns, or abrupt changes in fossil diversity. In short, almost everything that defines a civilization to us, their culture, their art, their architecture, would vanish. What would remain is invisible until carefully studied, and even then, it could be easily mistaken for natural processes. So when we ask whether humans are the first civilization, the unsettling answer is that even if we were not, there might be no way of knowing. Our own future legacy reminds us of this. If some intelligence were to dig through Earth's rocks 50 million years from now, would they see the towering cities we built, or would they only see chemical clues that suggest a species once rose, burned fuel, changed the climate, and disappeared? The more we study the fragility of evidence, the more we realize that permanence is an illusion. Earth itself is constantly rewriting its surface, and civilizations, no matter how mighty, are written in ink that fades far faster than we like to believe. When we look at the story of human history, it's tempting to think of ourselves as ancient. We talk about the glory of Rome, the achievements of Egypt, the philosophies of Greece, and the stone tools of prehistoric hunters as if they represent enormous stretches of time. And in a sense, they do, at least when compared to the human lifespan. A single person may live 70 or 80 years, so a civilization lasting thousands of years feels eternal in comparison. But when we zoom out and place human history against the timeline of the Earth, our achievements become almost laughably recent. Take a moment to think about this. Most of the technology that defines our modern world, the things that we associate with advanced civilization, has only existed for less than 2 centuries. The automobile was invented in the late 1800s. The airplane came into being in the early 20th century. The first computers didn't appear until the mid-20th century. Satellites, which now orbit our planet in the thousands, have been around for only about 65 years, beginning with Sputnik in 1957. The Internet, the vast digital nervous system of humanity, has existed for barely 3 decades in a form we'd recognize. Even electricity, which feels so fundamental to us now, only became widespread in the last 150 years. That means that almost everything we take for granted as civilization in the technological sense is so recent that it barely registers on any meaningful timescale outside our own. If we consider that Earth is 4.5 billion years old, our technological age has lasted less than 0.000004% of that time. To put it another way, if Earth's history was stretched across a single day, our entire technological age would last less than a fraction of a second before midnight. All of our skyscrapers, airplanes, cell phones, cars, and space missions, everything we imagine as symbols of our greatness, are just the briefest blink in the eye of geological time. Even agriculture, which feels like the foundation of human progress, is incredibly new. The shift from hunting and gathering to farming happened around 10,000 years ago, which seems ancient when we compare it to our lifespans. Yet even that span of time is only a tiny sliver of Earth's timeline. 400s of thousands of years before agriculture, Humans lived as small bands of nomadic hunter-gatherers, using stone tools and fire, but leaving behind very little in the way of lasting structures or technology. What we think of as history, the invention of writing, the rise of cities, the building of empires, occupies only the last few thousand years, a mere drop in an ocean of time. And here's the humbling part. When we look at how long dinosaurs dominated Earth, our entire story feels like a footnote. Dinosaurs reigned for over 160 million years, filling every ecological niche on the planet. In comparison, human civilization has existed for less than 0.01% of that time. Our entire species hasn't even reached 1 million years yet. Our technological civilization, which we are so proud of, has not even existed for a full 200 years. It is less than a blink compared to the lifespan of entire lineages of ancient life. This is what makes the idea of detecting other civilizations so difficult. If our signal as a technological society is so short and so fragile, then even if there had been another species before us that reached a comparable level of industry, their footprint might have been erased entirely. Imagine if a civilization had arisen 50 million years ago, during the Eocene epoch, when mammals were already flourishing after the extinction of the dinosaurs. Even if they had lasted tens of thousands of years, their entire technological window would still be nothing compared to the millions of years that followed. Their traces could have been eroded, buried, or destroyed in that span, just as ours would be if we disappeared tomorrow. We like to think that we've reached the pinnacle of permanence, that our satellites and space probes will drift through eternity as evidence of our presence. But even those will eventually decay, crash, or drift into the void. On Earth, our great achievements will vanish far sooner. The Hoover Dam, the Golden Gate Bridge, the Tokyo skyline, all would collapse and disappear in a geological instant. The human story, for all its complexity and brilliance, is almost invisible compared to the scale of the planet's history. The contrast between human history and geological time is, in many ways, the very heart of the Silurian Hypothesis. We've only just begun to leave a mark, and even that mark is so fragile that it might not last long enough to be noticed in the deep future. If our signal can fade so quickly, how much more difficult would it be to find the traces of another civilization, one that may have risen and fallen long before us? The gap between our sense of time and Earth's actual timeline makes it clear. Civilizations, no matter how advanced, are temporary notes in a symphony that has been playing for billions of years. If we're trying to imagine whether another civilization might have once existed on this planet millions of years before us, we have to reckon with a sobering truth. The fossil record is profoundly incomplete. In fact, it is so incomplete that the vast majority of living things that have ever walked, swum, or flown across Earth left no fossil trace whatsoever. The very idea that we could find evidence of a city, a tool, or a piece of technology from tens of millions of years ago becomes far less likely when you realize just how rare it is for even bones, shells, or leaves to survive the ages. Fossilization is not the norm, it is the exception. To understand this, let's think about what happens when most living things die. A bird might fall in a forest, a fish might die in the ocean, or a mammal might collapse on a plane. In almost every case, scavengers, microbes, and the elements quickly take over. Flesh decays, bones are gnawed apart or weather away, soft tissues vanish almost instantly, and in a matter of days or weeks, nothing recognizable remains. Even harder structures like bones or shells eventually crumble under the elements unless something extraordinary happens. For fossilization to occur, a creature usually needs to be buried very quickly in an environment where decomposition and disturbance are slowed, such as by sediment underwater, volcanic ash, or mudslides. And even then, the chances of preservation are still slim, because the remains must then endure the pressure of time, mineral replacement, and the constant churn of geology without being destroyed. The result of these harsh requirements is that the fossil record represents only a tiny sliver of life's true diversity. Paleontologists estimate that more than 99% of all species that have ever lived are extinct, and yet we only have fossils from a fraction of them. Most species left no trace at all. Even among the species that do leave fossils, the record is often fragmentary. A few bones here, a tooth there, maybe a partial skeleton if we're lucky. For many organisms, we have no complete skeletons, and for countless others, we have no evidence they ever existed at all. Imagine how many entire ecosystems, lineages, and unique creatures once thrived and disappeared without leaving behind a single clue. Now think about what that means for detecting civilizations. If whole species can vanish without leaving a trace, how much harder would it be to find traces of buildings, tools, or technologies? Fossilization favors bones, shells, and hard parts of organisms. It does not favor manufactured materials, which corrode, decay, or get recycled by Earth far faster than bone. Even if a city were to be buried in volcanic ash or submerged under the ocean, the chances of its structures fossilizing in a way that would last tens of millions of years are extraordinarily slim. Most of what we build would disintegrate before it had any chance of becoming fossilized. Consider the case of the dinosaurs. They dominated Earth for over 160 million years, living on every continent and producing countless species. Yet today, the fossil record only gives us glimpses of their reign. We know far more about certain groups than others, and even our best specimens are incomplete. Out of millions of individual dinosaurs that once lived, we found only a few thousand relatively complete skeletons. Many species are known only from a handful of bones. That's from creatures that lasted longer than almost any group of animals in history. If even their reign left only fragments, what would be left of a short-lived technological civilization? The incomplete fossil record also explains why new discoveries continue to rewrite our understanding of prehistory. Every time paleontologists dig, they unearth something that changes the story. A new feathered dinosaur that links birds to their ancient ancestors, a new primate that pushes back the origins of humanity, or a new marine fossil that reveals lost ecosystems. These discoveries remind us that what we don't know vastly outweighs what we do. The fossil record is not a clear book. It's a tattered manuscript with most of the pages missing. For the Silurian hypothesis, this rarity is central. If another civilization had once existed, the odds are overwhelming that it would not have left behind recognizable fossils of its people or its constructions. The chances that we would stumble upon a fossilized tool, a machine, or even a skeleton are vanishingly small. Instead, if anything remained, it would be subtle and indirect. Chemical residues, unusual isotopic signatures, or strange disruptions in sediment layers. The physical forms of their civilization would be erased, just as nearly all the species that have ever lived have been erased. This realization is humbling. It means that even if intelligent beings had once flourished here, our chances of finding clear, fossilized evidence of them are microscopic. The Earth forgets almost everything that has ever lived upon it. What survives is a tiny, distorted sample, a fragile whisper of a vast chorus that once filled the world. And so, when we look back through time and see only bones, shells, and stone, we must remember that these are not the full story. They are the scraps left behind after time has devoured almost everything else. If we expect to find traces of a long-lost civilization, we cannot count on fossils to tell the tale. When we think about traces of the past, it's natural to imagine them sitting quietly beneath our feet, waiting to be uncovered. We picture ruins preserved under layers of dirt, fossils sealed in stone, or artifacts lying dormant until archaeologists brush away the dust of time. But Earth is not a static museum. It is a restless, ever-changing system where continents shift, mountains crumble, and oceans open and close over vast expanses of time. This dynamic nature of the planet makes the survival of any evidence, whether biological or technological, an incredibly rare stroke of luck. If a civilization did exist millions of years ago, the processes of erosion and plate tectonics would have acted like relentless janitors, sweeping away nearly every trace of its presence. Erosion alone is a powerful eraser. Mountains, no matter how tall or imposing, eventually wear down under the persistent forces of wind, water, ice, and gravity. Rainfall cuts valleys into rock, rivers carry away sediment grain by grain, glacier. Grind landscapes flat, and coastal waves batter cliffs into sand. Even the grandest structures humans have built would not survive these natural forces for more than a few tens of thousands of years without upkeep, and certainly not for millions. Imagine our tallest skyscrapers, our massive dams, or even the pyramids of Giza. Eventually they would crumble into rubble, and that rubble would itself break down further until nothing recognizable remained. A mountain made of stone cannot resist erosion forever. How could a structure of steel and concrete hope to fare better across deep time? Now add plate tectonics into the equation, and the erasure becomes even more profound. Earth's crust is not fixed. It is broken into enormous plates that float atop the molten mantle below. These plates are constantly moving, colliding, separating, and grinding past one another. In some places, new crust is born as molten rock rises at mid-ocean ridges, pushing the seafloor apart. In other places, old crust is dragged down into the mantle at subduction zones, recycled into the interior of the planet. Over tens of millions of years, this process means that entire oceans disappear, continents drift across the globe, and entire landscapes are obliterated. The seafloor provides the clearest example. While we often think of the ocean floor as ancient and unchanging, in reality it is shockingly young. Because of seafloor spreading and subduction, the oldest parts of today's ocean floor are only about 200 million years old. That might sound like a long time, but compared to Earth's 4.5 billion year history, it's just a small fraction. Everything older than that has been swallowed back into the mantle. So, if a civilization had built vast cities or even left technological debris on the ocean floor 300 million years ago, none of it would remain today. The seafloor would have recycled it all, erasing every trace as if it had never existed. Even on land, tectonic activity reshapes the world. Mountains rise where plates collide, only to be worn down again by erosion. Continents split apart and recombine, scattering ancient terrains into new configurations. Volcanic eruptions bury landscapes under lava, while earthquakes grind rock into rubble. Over millions of years, these processes do not simply cover up the past, they fundamentally destroy it. The rocks themselves are melted, crushed, or transformed into new forms, obliterating whatever evidence may have once been contained within them. To get a sense of how thorough this process is, consider how little of Earth's surface actually preserves records older than a few hundred million years. Rocks from the Archean Eon, more than 2.5 billion years ago, are extraordinarily rare and usually highly metamorphosed, meaning they've been altered by heat and pressure so extensively that their original features are almost unrecognizable. Any traces of life or civilization from such times would be nearly impossible to identify. Even younger rocks often tell only partial stories, with layers missing, distorted, or destroyed by geologic forces. For us, this means that even if an advanced civilization had once existed and left behind monumental cities, great highways, or vast mining complexes, plate tectonics and erosion would conspire to erase them on a timescale of millions of years. Skyscrapers would collapse, debris would be buried, and the shifting Earth would recycle or grind it all away. The grandeur of such a civilization would eventually vanish, reduced to dust or magma. And unlike bones or shells, which at least have a chance of fossilizing, the concrete, metal, and glass of our world are not well suited for deep preservation. This is why the Silurian Hypothesis takes geology so seriously. The Earth is not static, it actively resists preservation. What we see today is not a faithful record of everything that has happened, but rather, the surviving scraps that happen to endure despite the constant churn of the planet. It's like trying to reconstruct the history of a library after its books have been burned, shredded, and rewritten countless times. The unsettling truth is that even if another civilization had once walked this earth, the very ground beneath our feet may have long since swallowed its story. The continents have shifted, the oceans have recycled their beds, and the mountains have risen and crumbled countless times. By now, only the faintest whispers, chemical traces, anomalies in the rock, could remain, if anything remains at all. If we follow this chain of thought deeper, we eventually arrive at one of the most haunting questions of the Silurian Hypothesis. If a civilization had once built great cities on Earth 100 million years ago, would we even be able to find their traces today? This question is both unsettling and strangely liberating, because it forces us to acknowledge how fragile the marks of civilization really are when measured against the backdrop of geological time. We often imagine cities as permanent fixtures, sprawling concrete jungles of glass, steel, and stone that will stand as long as humanity endures. But that permanence exists only on the human scale, not the planetary scale. Take the most iconic cities of our time: New York with its towering skyline, Tokyo with its endless neon and steel, Dubai with its futuristic architecture rising from the desert. To us, these places feel monumental and enduring. Yet if humans disappeared tomorrow, nature would begin reclaiming them almost immediately. Within years, vegetation would creep through cracks, wildlife would move into abandoned streets, and weather would start to wear away exposed structures. Without maintenance, buildings would collapse within centuries. Within tens of thousands of years, almost every visible trace of our cities would be gone, buried under soil, forests, or sand. And that's not even considering millions of years. Now stretch that timeline forward 100 million years, the timescale at the heart of the Silurian hypothesis. By then, continents will have drifted into new positions, mountain ranges will have risen and fallen, rivers will have carved new landscapes, and ice ages will have reshaped the world multiple times. Oceans will have opened and closed, swallowing coastlines and uplifting seabeds into new terrains. On such a timescale, the cities we take for granted today would not just be forgotten, they would be obliterated. Even the deepest foundations, the tallest skyscrapers, and the largest concrete structures would be pulverized, eroded, and recycled by the ceaseless machinery of geology. What about traces underground? Suppose an advanced civilization built cities of stone and metal and buried their dead in cemeteries, much like we do. Could these survive longer than the cities above ground? The problem is that even buried material doesn't stand much chance. Soil and rock layers shift over time, subject to pressure, chemical change, and groundwater movement. Organic materials like wood, cloth, or paper would vanish almost immediately. Metals corrode, especially in moist conditions, and over millions of years they return to the earth as oxides and ores. Concrete, while durable in human terms, crumbles under prolonged exposure to pressure and chemical alteration. In other words, what goes into the ground does not necessarily come back out intact. It transforms, erodes, or disappears entirely. So, if a civilization had indeed constructed skyscrapers and sprawling urban landscapes 100 million years ago, our odds of finding their remnants are extraordinarily low. We would not stumble upon recognizable skyscraper ruins. We would not find intact bridges or highways stretching across fossilized landscapes. We would not uncover their monuments, standing tall like our pyramids or Stonehenge. At best, we might encounter subtle anomalies in geology, layers of unusual sediments that don't match the natural processes of the time, traces of metals or compounds in concentrations too high to be explained by ordinary means, or other indirect fingerprints of industry. But skyscrapers themselves? They would be gone, erased as surely as if they had never been. The problem becomes even more striking when we compare the lifespan of cities to the age of Earth itself. Modern cities, as we know them, are scarcely more than a few thousand years old. Industrial cities with steel and concrete are only about 200 years old. Yet Earth is 4.5 billion years old. To expect a city to survive visibly across millions, or even tens of millions, of years is like expecting a footprint in the sand to survive a tidal wave. The natural processes of erosion, tectonics, and climate cycles act like an unstoppable reset button, returning the surface of the Earth to a blank slate again and again. This is why the Silurian hypothesis asks not whether we could find skyscrapers or highways, but whether we could detect indirect signatures, things like chemical residues, isotopic anomalies, or peculiar mineral formations. The physical architecture of cities is fleeting, no matter how advanced the civilization that builds them. The real question is whether the activities of those cities leave a lasting fingerprint in the geological record. And even then, those fingerprints could be incredibly hard to distinguish from natural events like volcanic eruptions, asteroid impacts, or massive climate shifts. So when we ask, if a civilization built skyscrapers 100 million years ago, would we find any evidence today? The sobering answer is, almost certainly not, at least not in the form we imagine. The skyscrapers themselves would be dust. The roads would be gone. The artifacts would be corroded beyond recognition. The grandeur of their architecture would have vanished. What might remain are shadows, chemical echoes in rock layers, unexplained shifts in isotopes, or puzzling anomalies that suggest something unusual once happened. But whether those shadows could ever be definitively linked to a vanished civilization is a mystery far more complex than digging up ruins. It requires reading Earth's rocks like cryptic messages from a forgotten past, knowing full well that time has done everything in its power to erase the message entirely. If skyscrapers and cities are destined to crumble into dust and vanish without leaving a recognizable trace, perhaps the key lies not in the monuments civilizations leave behind, but in the byproducts of their industry. Every advanced society, including ours, reshapes its environment not just through architecture and construction, but through chemistry, introducing substances into the air, water, and soil that would never exist naturally or would exist only in vanishingly small quantities. This is where the Silurian hypothesis takes an intriguing turn. If we can't hope to find buildings from a civilization 100 million years ago, perhaps we could still detect the unique chemical fingerprints they left behind in the geological record. Consider plastics, one of the defining materials of our time. Plastic is everywhere, in our packaging, our clothing, our tools, our electronics, even in the microscopic fibers floating in the ocean and drifting in the air. Unlike stone or metal, plastic does not occur naturally in significant amounts. It is the product of deliberate industrial activity. Over time, plastics degrade into smaller and smaller particles called microplastics, which are now so widespread that they've been found in Arctic ice, deep ocean trenches, and even inside the bodies of living organisms. In fact, we are creating a global layer of plastic pollution so persistent that geologists have already suggested it could serve as a marker for the Anthropocene, the proposed new epoch defined by human impact on Earth. But here's the catch: while plastics are durable on human timescales, they may not survive for millions of years. Sunlight breaks them down, microbes consume them, and heat and pressure in the earth transform them into something unrecognizable. Yet, some portion might survive, not as intact bottles or wrappers, but as chemical residues embedded in sediments. Plastics are made from synthetic polymers, many of which contain chemical bonds that don't form in nature. Even if the material itself is gone, its breakdown products could remain trapped in rock layers. So, if a civilization millions of years ago had its own version of plastics, perhaps we'd still find hints of their existence. Not a toy or a bag, but a strange, persistent chemical signature that doesn't quite belong. Beyond plastics, there are countless synthetic compounds we've introduced into the environment that nature simply doesn't make on its own. Think of industrial chemicals like PCBs, polychlorinated biphenyls, pesticides such as DDT, or refrigerants like CFCs. These substances have long half-lives and spread globally, becoming detectable even in places far from their point of origin. They are what scientists call persistent organic pollutants, chemicals that resist natural degradation and accumulate in ecosystems. Even if they eventually break down, the altered chemical structures they leave behind could serve as a red flag for future geologists looking back at our time. If another civilization millions of years ago created its own suite of synthetic compounds, those molecules, or at least their byproducts, might still lurk in ancient sediments, long after everything else has vanished. Then there is heavy metal pollution. Industrial processes, from mining to manufacturing, release unnatural concentrations of elements like lead, mercury, cadmium, and arsenic into the environment. Normally, these metals are present in small amounts, locked safely in rock. But when industry extracts and disperses them, they end up in rivers, soils, and oceans, creating concentrations that stand out from natural levels. For example, the leaded gasoline era of the 20th century spread lead particles across the globe, depositing them in ice cores and sediment layers that scientists can still detect today. These traces will endure as a distinct marker of our industrial activity. If some other civilization mined and processed metals millions of years ago, we might expect to see similar anomalies. Layers of rock with unexpected spikes in heavy metal concentrations that can't easily be explained by volcanic activity or asteroid impacts. Even coal and oil burning leaves behind telltale signatures. When we burn fossil fuels, we don't just release carbon dioxide. We also scatter trace amounts of rare elements like vanadium, nickel, and chromium. These settle into sediments, leaving a thin chemical fingerprint of industrial combustion. In the far future, geologists may find these spikes in ancient rocks and wonder about their origin. Could they mistake them for natural processes, or would they recognize them as the work of a technological civilization? That uncertainty is precisely why the Silurian hypothesis exists, not to claim such civilizations did exist, but to explore how we could distinguish between natural and artificial signatures in deep time. What makes industrial byproducts so important is that they represent a kind of unintentional fossil. Cities crumble, technology rusts, and artifacts vanish, but the chemical changes we impose on the environment are harder to erase. The Earth absorbs them, locks them into layers, and sometimes preserves them for millions of years. If another civilization had its own plastic age or equivalent, it's possible that subtle chemical residues would still be hidden in the strata, waiting to be uncovered. But, of course, nature can be tricky. Volcanic eruptions, asteroid impacts, and other massive events also leave behind unusual chemical layers. Differentiating between the byproducts of industry and the byproducts of natural cataclysms is not simple. That difficulty is what makes this thought experiment so tantalizing. In the end, industrial byproducts may be the best bet for detecting a long-vanished civilization. Not their art, not their architecture, not even their bones, but the unintended pollution they left behind. If we vanish tomorrow, it won't be our skyscrapers or satellites that tell the story of humanity to whatever comes next. It will be the stubborn chemical echoes of our presence, a thin plastic-stained layer of rock, a spike of heavy metals, a strange cocktail of synthetic compounds that no volcano or asteroid could produce. That might be the true fossil of an industrial age, and if anyone were to look deep into Earth's history for evidence of another civilization, that is where they would have to search. One of the most subtle yet powerful fingerprints an industrial civilization can leave behind isn't something you can see with the naked eye, like a crumbling building or a rusted piece of machinery. It's something written in the chemistry of the air, the oceans, and the rocks themselves. Specifically, it's the way the balance of carbon isotopes shifts when fossil fuels are burned. This is a detail so delicate that it requires scientific instruments to detect, yet it could be one of the most enduring markers of industrial activity, potentially persisting for millions of years after everything else has been erased. To understand this, let's break it down. Carbon, the backbone of life and industry, comes in several isotopic forms, atoms that are chemically identical but differ in weight. The most common isotopes are carbon-12 and carbon-13. Plants, which form the base of fossil fuels, prefer to absorb the lighter isotope, carbon-12, during photosynthesis. Over millions of years, as plants died and became buried, their carbon-12 rich remains transformed into coal, oil, and natural gas. This means fossil fuels contain unusually high concentrations of carbon-12 compared to carbon-13. Now fast forward to the industrial age. When humans began burning vast amounts of fossil fuels, we started releasing this carbon-12 heavy material back into the atmosphere. The result? The ratio of carbon-12 to carbon-13 in the atmosphere began to shift noticeably. Scientists call this the Seuss effect, and it's one of the clearest signals that the rise in atmospheric carbon dioxide is not just a natural cycle, but directly tied to human industrial activity. Ice cores, tree rings, and modern air samples all show this distinctive isotopic fingerprint. Here's where things get interesting for the Silurian hypothesis. If another industrial civilization existed millions of years ago and relied heavily on burning fossil fuels, whether coal, oil, or some equivalent energy source, they too would have altered the balance of carbon isotopes in the atmosphere and oceans. That shift could, in theory, leave a detectable trace in the geological record, preserved in carbonate rocks, deep sea sediments, or even the fossilized remains of organisms that lived during that time. Just as geologists today can detect isotope shifts from ancient volcanic eruptions or climate events, they might also be able to pick out the subtle signature of industrial carbon burning, even tens of millions of years later. Of course, this is where the mystery deepens. Natural processes can also cause carbon isotope anomalies. For example, massive volcanic eruptions can release carbon into the atmosphere, and methane clathrate releases from the ocean floor can trigger dramatic climate changes. These events also shift carbon isotope ratios, often in ways similar to fossil fuel burning. So the question becomes, could we tell the difference between a natural carbon isotope shift and one caused by an industrial civilization? That's not an easy question to answer. The patterns may overlap, and without corroborating evidence, it's hard to say whether an anomaly is technological or geological. One fascinating example comes from an event known as the Paleocene-Eocene Thermal Maximum, or PTM, which happened about 56 million years ago. During this period, global temperatures spiked dramatically, and there was a sudden release of carbon into the atmosphere, as recorded in the isotope ratios. Some scientists speculate that this event could serve as a kind of test case for the Silurian hypothesis. Was the PTM simply the result of natural methane releases and volcanic activity? Or, if we stretch our imaginations, could it have been the industrial footprint of a lost civilization? The mainstream explanation is natural processes, of course, but the fact that the question can even be raised highlights just how difficult it is to distinguish between industrial and natural isotope signals in deep time. Still, the persistence of isotope anomalies makes them one of the strongest candidates for detecting vanished civilizations. Unlike plastics or metals, which can degrade, or buildings, which crumble, isotope ratios are recorded in the chemistry of rocks themselves, locked into layers of stone that endure for millions of years. They don't need to be preserved as objects, they are encoded into the very foundation of the Earth's geological memory. Now imagine future geologists, tens of millions of years from now, examining the rocks of our present age. They would notice a sharp, unusual shift in the carbon isotope record beginning around the 18th century and accelerating into the 20th and 21st centuries. They would see the spike in carbon dioxide levels, the drop in carbon-13 relative to carbon-12, and the warming of global temperatures that followed. To them, it would be a puzzle. What caused this sudden chemical imbalance in the carbon cycle? Was it a natural catastrophe, or was it the industrial footprint of a civilization that briefly flourished before disappearing? That is precisely the same puzzle we would face if we ever encountered such an anomaly in rocks dating back 100 million years or more. This is why isotope anomalies hold such weight in discussions of the Silurian hypothesis. They offer a durable, measurable, and global signal, something that doesn't rely on the survival of artifacts or architecture but is etched into the deep time of Earth itself. Yet they also highlight the challenge of interpretation. Even if we did find such a signal, how could we ever be certain it was the result of technology rather than geology? That ambiguity is part of what makes the hypothesis so fascinating. It forces us to confront the limits of what we can know about the past, while also reminding us that our own civilization is leaving behind such a signal right now. When we talk about the legacy of civilizations, most of what we imagine, monuments, tools, artwork, or even cities, fades away quickly in geological terms. But there's one category of technology that has the potential to outlast nearly everything else: nuclear activity. Unlike plastics or metals, which degrade, nuclear reactions alter matter itself, leaving behind isotopes and radiation scars that can persist for hundreds of thousands, sometimes even millions, of years. If another civilization rose and mastered nuclear technology long before humanity, the traces of their reactors, weapons, or accidents might still be faintly detectable in Earth's rocks today. The most obvious starting point is nuclear reactors. Humanity's reactors produce a wide array of artificial isotopes that simply don't occur in nature, or at least not in the concentrations we create. Take plutonium-239, for instance. This isotope doesn't exist naturally in measurable amounts on Earth. It's a product of nuclear reactions, with a half-life of about 24,000 years. On the scale of deep time, that might sound fleeting, but in geological layers it's long enough to leave behind a detectable trace for tens of thousands of years after it was produced. Other isotopes, like certain cesium and strontium variants, are also byproducts of fission, and they end up embedded in soils and sediments wherever fallout occurs. Now, most of these isotopes decay away after a few million years at most. That means if a civilization had nuclear technology 100 million years ago, the isotopes themselves would have long vanished. But here's the interesting part: their decay products remain. When a radioactive isotope breaks down, it doesn't disappear into nothing. It transforms into another element, often in ratios that don't quite match what natural geology would produce. For example, unusual concentrations of certain lead isotopes can signal the former presence of uranium or thorium decay chains. These kinds of geochemical oddities could, in theory, flag the remnants of ancient nuclear activity. Weapons, too, leave scars. Nuclear detonations don't just release isotopes, they fundamentally alter the structure of minerals and soils in ways that persist. For example, the intense heat of a nuclear blast fuses sand into a kind of glass called trinitite, famously left behind at the Trinity test site in New Mexico. This fused material is unlike anything formed in ordinary natural processes, though, to be fair, lightning strikes can also create glassy fulgurites, and meteor impacts produce their own shock-fused minerals. Still, nuclear blasts leave behind a unique combination of isotopes and mineral structures that future geologists would recognize as technological. Even if the isotopes decay, the strange mineralogical fingerprints could remain much, much longer. Then there's the question of nuclear accidents. Take Chernobyl or Fukushima. Both sites released radioactive isotopes into the surrounding environment, seeping into soils, rivers, and oceans. Over time, much of the radioactivity will fade, but the altered isotopic ratios and the subtle changes in mineral chemistry could remain as a permanent marker in the geological record. If we extrapolate this idea, a civilization that suffered large-scale nuclear accidents, or worse, engaged in nuclear warfare, would leave behind a widespread, planet-altering signature, a chemical fingerprint smeared across the rock layers of their time. But here's where the mystery deepens. Earth itself sometimes produces phenomena that resemble technological traces. In Gabon, Africa, scientists discovered the remains of what they first thought might have been an ancient reactor, but it turned out to be a natural one. Roughly 2 billion years ago, conditions in uranium-rich deposits allowed spontaneous nuclear fission to occur underground. These natural reactors burned steadily for hundreds of thousands of years, leaving behind depleted uranium and other isotopic changes very similar to what human reactors produce. This discovery proves that nature, under the right circumstances, can mimic what we would normally consider a technological trace. So if we were to find strange nuclear signatures in rocks from 100 million years ago, would we be able to confidently say, yes, this must be evidence of an ancient civilization? Or would we have to admit that natural processes could be responsible? That ambiguity is precisely what makes nuclear traces so fascinating. On the one hand, they are among the clearest markers of advanced technology, a literal rewriting of the elements. On the other hand, the fact that natural processes can occasionally produce similar effects muddies the waters. Still, many scientists argue that the specific mix of isotopes created by widespread nuclear technology, particularly those from bomb testing, would be unique enough to stand out, at least for tens of millions of years. If a long-gone civilization had unleashed nuclear energy on a global scale, it's hard to imagine no trace of that activity surviving in some form. Looking forward, if humanity were to vanish tomorrow, one of our longest-lasting legacies might not be our skyscrapers or satellites but the nuclear signatures buried in the rocks. Even long after our cities crumble and our plastics degrade, the isotopic scars of our reactors and weapons tests will linger, whispering to the future that an advanced civilization once lived here. Which raises the chilling question: if another civilization had once walked this earth and mastered the atom, would we even notice their whispers today? Or have their traces already been misinterpreted as natural oddities in the geologic record? When people imagine the traces of a vanished civilization, they often think of great monuments, shining towers, or colossal machines. But in reality, one of the most enduring legacies of industrial activity isn't what we build, it's what we take away. Mining is the act of carving into the bones of the planet itself, extracting metals, minerals, and fossil fuels on scales so vast that entire landscapes are reshaped. If an advanced civilization lived millions of years before us, one of the best chances we might have of detecting them would come not from their surviving artifacts, but from the scars left behind by their hunger for resources. Think about the modern world for a moment. Humanity has dug enormous open-pit mines, some stretching kilometers across and hundreds of meters deep. We have bored tunnels into mountains, stripped away entire hillsides, and dredged the ocean floor for minerals. Copper, iron, coal, rare earth elements, uranium, all have been extracted in staggering quantities. From space, some of these mines are already visible as gaping wounds in the Earth's surface. Even if our cities collapsed and were erased by time, these enormous excavations might persist longer, etched into the geology itself. But here's the twist: the Earth is a master of self-repair. Over millions of years, erosion can fill in open pits, vegetation can reclaim disturbed areas, and sediments can bury vast mining operations. Plate tectonics, grinding away across geologic timescales, can recycle entire crustal plates, swallowing up evidence in subduction zones and spitting it back out as new rock. What looks like a scar today may be nothing more than an unrecognizable wrinkle in the rock record a few million years from now. Still, certain signatures could endure. For example, when humans mine metals, we concentrate and redistribute elements in ways that don't occur naturally. Take aluminum. It's abundant in Earth's crust but rarely found in pure, usable form. Industrial smelting produces refined aluminum that can later scatter into soils and sediments. Over deep time, even if the refined metal corrodes away, the unusual chemical distribution it leaves behind could persist. Similarly, heavy mining of copper or rare earth elements could create localized anomalies, areas where the natural balance of elements in the crust looks strangely depleted or rearranged. A future geologist could stumble upon such a deposit and wonder, was this the work of tectonic activity, or the fingerprints of intelligent hands? Coal mining offers another striking example. In many places, we've stripped away thick seams of ancient vegetation, leaving behind layers of disturbed geology. Open-pit coal mines, in particular, carve enormous bowls out of the landscape. Millions of years from now, the coal itself may be gone, the pits filled in, but the disrupted stratigraphy, the out-of-place arrangement of rock layers, could remain as a clue that something unusual once happened there. Even more intriguing is uranium mining. Because uranium ore is relatively rare and tightly concentrated, the extraction of large amounts can leave behind a distinct geochemical signature. Imagine an ancient civilization that mined uranium not just for energy but perhaps for weapons. The isotopic patterns left behind, pockets of depleted or scattered through otherwise untouched deposits, could remain frozen in the rock for hundreds of millions of years. To a modern geologist, it might look like an anomaly, a puzzle piece that doesn't quite fit with the story of natural processes. Yet, once again, the challenge is interpretation. Natural processes can also mimic the effects of mining. For example, erosion and groundwater flow can redistribute metals in peculiar ways, creating depleted or enriched zones that resemble industrial extraction. As we saw with the natural nuclear reactors of Gabon, Earth itself sometimes produces patterns we might mistakenly attribute to intelligence. This blurring of lines between natural and artificial is exactly what makes the Silurian hypothesis such a compelling thought experiment. If we discovered what looked like an ancient mine, how would we know it wasn't just an unusual quirk of geology? Now imagine a future civilization, tens of millions of years from now, digging into the Earth's crust and finding the traces of our own mining operations. They wouldn't find bulldozers or drills preserved in stone, but they might notice patterns. Enormous regions where metals like copper are strangely absent, or vast disturbed layers where coal seams should have been. They might notice isotopic distributions of lead or uranium that don't align with natural decay processes. From these subtle clues, they could begin piecing together the idea that some form of intelligence once reshaped the geology of the planet. And that brings us back to the question at the heart of the Silurian hypothesis. If another civilization once mined the Earth millions of years before us, would we even know? Could there be strange chemical scars in the crust, misfiled by geologists as odd natural anomalies, that are actually the fossilized traces of industry? The idea forces us to see our own activity in a new light, as something that may one day look indistinguishable from natural processes to distant eyes. When we look into the fossil record, we see a story of life written in fragments, moments frozen in stone that hint at the rise and fall of countless species. Most of the time, this record reflects slow, gradual changes. Species evolve, adapt, or disappear as environments shift. But then, there are the sudden breaks, sharp, dramatic events when vast numbers of species vanish in a geological instant. These are the mass extinctions, and they stand out like punctuation marks in Earth's history. Dinosaurs wiped out at the end of the Cretaceous, trilobites disappearing after the Permian extinction, countless marine species lost at the close of the Ordovician. Each of these catastrophic events leaves a glaring gap in the fossil record, a moment when life stumbled. Traditionally, scientists explain these gaps through natural disasters, asteroid impacts, massive volcanic eruptions, runaway climate change. The Cretaceous-Paleogene extinction, for instance, is linked to a colossal asteroid impact in what is now the Yucatan Peninsula. The Permian extinction, the deadliest event in Earth's history, appears to have been fueled by immense volcanic activity in Siberia, releasing enough carbon dioxide to superheat the planet. These natural causes are well supported by evidence. But when we overlay the Silurian hypothesis onto this picture, a provocative question arises. Could some of these sudden die-offs have been triggered not by nature, but by the industrial activity of a forgotten civilization? Think of it this way. Humanity, in just a few hundred years of industrialization, has already pushed the planet toward a climate crisis. We've raised atmospheric carbon dioxide to levels not seen in millions of years, we've acidified the oceans, and we've triggered what many biologists now call the sixth mass extinction. Species are disappearing today at rates comparable to the great die-offs of prehistory, and it's all happening within a blink of geological time. If future geologists studied our era millions of years from now, without knowing anything about humans, they might simply observe a sudden spike in extinctions, a dramatic shift in climate, and a strange chemical signature in the rocks. Would they assume it was caused by industrial civilization, or would they blame it on a natural catastrophe, just as we do when we look back at earlier events? This is where unusual fossil gaps become especially intriguing. For example, Consider the Paleocene-Eocene thermal maximum, PETM, about 56 million years ago. During this event, Earth's temperature spiked dramatically, the oceans warmed, and ecosystems were upended. In the fossil record, we see abrupt changes in species distribution and extinctions. The cause is still debated: massive volcanic activity, methane release, or some other natural carbon injection. But under the Silurian hypothesis, one could at least ask whether this pattern, rapid climate change, carbon isotope anomalies, and extinctions, might resemble what we'd expect from an ancient industrial civilization. To be clear, no evidence supports that interpretation, but the resemblance forces us to consider how similar our modern fingerprint is to those ancient mysteries. The same logic could apply to other extinction events. If a hypothetical civilization had reached industrial capacity millions of years ago, their activities could have triggered extinctions through climate shifts, habitat destruction, or chemical pollution. They might have used fossil fuels, altering the balance of carbon isotopes in the atmosphere just as we have. They might have introduced synthetic compounds or metals into the environment, leaving subtle traces in the sediment layers. And when their civilization collapsed, whether from self-destruction or natural disaster, the biosphere might have carried the scars in the form of sudden die-offs and ecological upheaval. The key challenge is that the fossil record is incomplete and biased. Fossilization is rare, selective, and patchy, meaning we often only see snapshots rather than continuous sequences. Many gaps may be due simply to missing evidence rather than catastrophic events. But in some cases, the abruptness of the change is undeniable. It's these moments, when a thriving ecosystem suddenly crashes, that spark the imagination. If our species disappeared tomorrow, future geologists would find a fossil record with abrupt gaps. Forests cut down, coral reefs vanished, megafauna wiped out, and countless smaller species gone. The record would look much like it does during past extinction pulses. The difference is that, in our case, the cause is undeniably tied to industrial civilization. So the question becomes, when we look back at the abrupt fossil gaps of the past, are we absolutely certain they were only natural in origin? Or could one of them, just one in that immense timescale, carry the ghostly imprint of something more? Even if we say probably not, the fact that we must acknowledge the similarity between today's extinction crisis and those in the distant past is telling. It reveals just how easy it would be for an industrial civilization to rise, burn brightly for a geological moment, trigger chaos in the biosphere, and then vanish, leaving behind nothing more than a sudden absence in the fossil record, a puzzle piece that future species would try to explain without ever suspecting the hand of intelligence behind it. When exploring mysteries as vast as Earth's deep history, there's always the temptation to leap toward the most dramatic explanation. The idea of an ancient industrial civilization, lost to time and buried under eons of geology, is undeniably thrilling. It sparks the imagination, ignites curiosity, and pulls us into a story of hidden worlds and forgotten epochs. But science isn't built on thrill, it's built on evidence, and when evidence is scarce, scientists often lean on a principle called Occam's razor. This principle, named after the 14th century philosopher William of Ockham, essentially says, when faced with competing explanations, the simplest one that accounts for all the facts is usually the correct one. Now, let's apply this to our discussion. When we encounter strange events in Earth's past, like sudden extinctions, unusual carbon spikes, or anomalies in the rock record, we have at least two possible interpretations. One is that these are the fingerprints of a lost industrial civilization. The other is that they are the products of natural forces, volcanism, asteroid impacts, oceanic changes, or shifts in climate caused by orbital variations. The second explanation doesn't require assuming the rise and fall of an advanced species that left no trace of itself, whereas the first requires us to imagine a civilization so elusive that it vanished almost without a whisper. Occam's razor, then, guides us toward the natural explanation as the more likely option. That doesn't mean the lost civilization idea is impossible. It just means it isn't necessary to explain what we already observe. Take the PETM, for example, the warming event 56 million years ago. The simplest explanation involves volcanic activity releasing massive amounts of greenhouse gases, and there is geological evidence supporting that view. Introducing a speculative industrial civilization into the equation doesn't add explanatory power. It complicates the picture without providing additional evidence. By Occam's razor, the volcanic theory remains stronger. This principle also protects us from our own biases. Human beings love stories. We're natural storytellers, always trying to weave patterns out of chaos. The thought of a forgotten civilization appeals to that instinct, but just because an explanation feels exciting or resonates with our imagination doesn't make it the most accurate. The universe often works in ways that are indifferent to our narrative preferences. When we see a crater, the simplest explanation is a meteorite, not a lost war between ancient superpowers. When we see a mass extinction, the simplest explanation is a natural catastrophe, not industrial pollution from a species we've never otherwise detected. It's worth remembering that the Silurian hypothesis itself isn't presented as evidence of a past civilization. The scientists who proposed it made this very clear. It's not about claiming that one existed, it's about sharpening our tools of detection. If we can imagine how such a civilization might leave traces, we can become better at distinguishing between natural processes and the fingerprints of intelligence, whether on Earth or on distant planets. Occam's razor remains the guiding rule: only invoke the extraordinary when the ordinary truly fails to account for what we see. But let's pause and reflect on the nuance here. Just because the simplest explanation is usually correct doesn't mean it is always correct. Occam's razor isn't a law of nature, it's a rule of thumb. It keeps us grounded, but it shouldn't stop us from asking questions at the edges. If, one day, we discovered a chemical anomaly or a geological feature that really couldn't be explained by known natural processes, then the extraordinary might have to be considered. In that case, the balance would shift, and Occam's razor might lead us toward the hypothesis of intelligence, not away from it. In the meantime, though, the natural explanations for mass extinctions, isotope shifts, and fossil gaps remain strong. Massive volcanic eruptions, asteroid impacts, shifting oceans, and plate tectonics can account for the evidence we see without requiring a vanished civilization. These forces are powerful, well understood, and demonstrably capable of reshaping life on Earth. They don't need the intervention of an advanced species to explain the story recorded in stone. And so, until the evidence demands otherwise, the simplest story remains the one written by nature itself. Throughout Earth's history, life has been both fragile and resilient, vulnerable to sudden catastrophes yet capable of rebounding in astonishing ways. When we examine the fossil record, some of the most striking moments are the mass extinctions, those intervals when vast numbers of species vanish in what seems like the blink of an eye. These are not subtle shifts in biodiversity but seismic collapses, moments when ecosystems that had flourished for millions of years abruptly broke apart. Now, while the Silurian hypothesis tempts us to wonder if an ancient civilization could have played a role in such disasters, the truth is that science already has powerful and well-supported explanations for why these events occurred, and they don't require invoking intelligent life at all. Let's begin with the most famous of all mass extinctions, the end of the Cretaceous period, around 66 million years ago. This is the event that brought an end to the age of dinosaurs and paved the way for mammals, and ultimately humans, to rise. The culprit? A massive asteroid impact. The evidence is overwhelming. Geologists have found a thin layer of iridium-rich clay at the boundary between the Cretaceous and the Paleogene periods. Iridium is rare in Earth's crust but common in asteroids, a telltale fingerprint of extraterrestrial impact. Further, scientists discovered the Chicxulub crater in the Yucatan Peninsula, a 150-kilometer wide scar left by the colossal impact. The energy released by that collision was billions of times greater than any human-made explosion. The aftermath: wildfires, acid rain, darkness from atmospheric dust, and global cooling, wiped out nearly 3/4 of species on Earth. No hidden civilization is needed to explain it. The asteroid alone did the work. Now consider the Permian-Triassic extinction, often called the Great Dying. Occurring around 252 million years ago, it was the deadliest event in Earth's history, erasing up to 90% of marine species and 70% of terrestrial species. The leading explanation here isn't an asteroid but volcanic activity on an almost unimaginable scale. In Siberia, enormous volcanic eruptions created what we now call the Siberian Traps, vast layers of basalt rock that stretch for millions of square kilometers. These eruptions lasted for hundreds of thousands of years, pumping out staggering amounts of carbon dioxide, methane, and other greenhouse gases. The result was runaway climate change, ocean acidification, and oxygen depletion in the seas. Entire ecosystems collapsed, and it took millions of years for life to recover. Again, natural forces alone are more than enough to explain the devastation. Another major event was the late Devonian extinction, about 375 million years ago. Unlike the sudden catastrophe of the asteroid impact, this extinction seems to have unfolded over several million years in a series of pulses. Hypotheses include widespread ocean anoxia, meaning oxygen levels plummeted, possibly driven by volcanic eruptions, nutrient runoff, or even the rise of the first large forests, which altered the balance of carbon dioxide and soil nutrients. No technology, no industry, just the natural dynamics of a changing planet that at times can turn hostile even to its own inhabitants. The Ordovician Silurian extinction, around 443 million years ago, offers yet another example. Here the evidence points to dramatic shifts in climate. The Earth entered a severe ice age, likely triggered by the growth of massive glacier as carbon dioxide levels dropped. Sea levels fell, habitats disappeared, and nearly 85% of marine species were wiped out. Eventually, warming followed, causing further ecological upheaval. This entire cycle was driven by planetary rhythms and geological processes, not by any intelligent interference. What's striking about all these events is not only their severity but also their variety. Asteroids, volcanism, climate shifts, and oceanic changes. Each of these natural mechanisms has, at different times, acted as a scythe sweeping through the tree of life. They demonstrate that Earth doesn't need help from advanced civilizations to periodically reset the biological clock. Catastrophe is built into the planet's nature, woven into its geological and cosmic fabric. That doesn't mean the Silurian hypothesis is irrelevant here. On the contrary, by comparing the effects of our modern industrial age with past events, we gain insight into how an intelligent civilization might leave its mark. Today, our burning of fossil fuels, our deforestation, and our chemical pollution are creating changes that, if seen millions of years in the future, might look a lot like some of these mass extinctions. The key difference is intent. Ours is driven by industry, while the ancient extinctions appear to be the inevitable outcome of natural cycles and sudden catastrophes. So, when we look back at the fossil record and see those great die-offs, the most straightforward explanation remains natural disaster. An asteroid's impact, a volcanic outburst, or a planetary climate swing can and has erased vast chapters of life without the need to invoke hidden civilizations. Occam's razor reminds us that the simpler story is usually the right one, and Earth's own natural violence provides all the tools necessary to explain the tragedies etched into its deep past. When people imagine the remnants of our civilization millions of years from now, they often picture endless seas of plastic bottles or corroded skyscrapers standing as eerie monuments to human industry. It's a haunting thought, our waste outlasting us, surviving as proof of our presence long after we're gone. And yes, plastics are durable, resistant to natural decay, and already choking ecosystems across the globe. Steel and concrete structures seem immovable in our lifetimes, looming giants of progress. But when you stretch the timescale to millions of years, the very scale we've been exploring, the permanence of these materials begins to dissolve. Our cities and landfills, our monuments and machines, may not leave much more behind than faint chemical whispers in the rock record. Take plastic, for instance. In our daily lives, it feels nearly indestructible. A plastic bag can linger in the ocean for decades, and microplastics are now found everywhere from the depths of the Mariana Trench to the ice of Antarctica. But plastics are polymers, long chains of carbon and hydrogen, and they are ultimately vulnerable to the twin forces of time and geology. Exposed to sunlight, plastic breaks down through photodegradation. Buried underground, bacteria and chemical reactions slowly gnaw away at its structure. In the deep oceans, where much of our plastic waste sinks, pressure and chemical interactions accelerate fragmentation. Over thousands of years, plastics might degrade into microscopic particles. Over millions, they may vanish entirely, leaving only faint residues or altered chemical signatures. To a geologist digging through ancient sediments tens of millions of years from now, plastic as we know it may be unrecognizable, dissolved into nothing more than an unusual concentration of carbon compounds. Metals face a similar fate. Steel beams, which today form the skeletons of our skyscrapers and bridges, are forged through processes that give them immense strength. Yet steel is ultimately just iron mixed with other elements, and iron loves to return to its natural oxidized state, rust. Given enough time, even the strongest steel corrodes. Picture a skyscraper left untended for a few centuries. The glass shatters, the steel rusts, the concrete cracks. Now extend that process across tens of thousands, hundreds of thousands, and finally millions of years. Weathering, water, and shifting geology don't preserve, they erase. Eventually, what was once a towering structure becomes nothing more than dust mixed into the soil, indistinguishable from the natural iron deposits scattered throughout the planet. Concrete, another symbol of human permanence, also deceives us with its apparent endurance. Yes, Roman concrete structures like aqueducts and harbors have lasted for over 2,000 years, a testament to its resilience. But 2,000 years is nothing in geological time. Concrete slowly reacts with water and carbon dioxide, weakening its bonds. Freeze-thaw cycles fracture it, while tectonic movements grind it back into the crust. Given enough time, concrete doesn't fossilize, it crumbles, and its distinct properties vanish. Even glass, which can last much longer than many other materials, would eventually be destroyed. While shards might survive for thousands or even millions of years, they too would ultimately weather down, crushed by geological processes or buried beneath sediment, transforming into silica indistinguishable from natural sand. Now think about our landfills. Billions of tons of human waste, plastics, metals, and electronics are buried there. In the near term, those sites are strikingly unnatural. But fast forward millions of years, and plate tectonics will have carried most of them deep into Earth's mantle, recycling them entirely. Others will erode, wash into the sea, or be buried so deeply beneath layers of sediment that only subtle chemical traces remain. If some future geologist stumbles across an ancient landfill site, what they'd find might not be recognizable objects but peculiar concentrations of carbon, synthetic molecules, or heavy metals embedded in the strata. The unsettling truth is this: even though we are currently transforming Earth in profound ways, time itself erases almost everything. The pyramids of Egypt, the Great Wall of China, the skyscrapers of New York City. On human timescales, they feel eternal. On geological scales, they are temporary blemishes. A few million years from now, the most enduring traces of our civilization may not be buildings, machines, or monuments, but thin chemical anomalies in rocks, small signals that only a highly trained eye would recognize as something unusual. And that brings us back to the Silurian Hypothesis. If our own plastic, metals, and constructions might vanish almost without a trace after just a few million years, then what chance would another industrial civilization, perhaps one that lived 100 million years ago, have of leaving behind recognizable evidence? The absence of visible ruins isn't proof of absence. It's simply what happens when time and geology get the final say. Let's take a moment to step far outside ourselves, not just centuries or millennia into the future, but into the truly unimaginable stretches of geological time. Picture Earth not tomorrow, not 10,000 years from now, but 100 million years ahead. By then, the continents will have shifted dramatically, as tectonic plates crawl across the planet's surface at their steady pace of a few centimeters per year. Oceans will have opened and closed, mountains will have risen and crumbled, glacier will have come and gone, and entire ecosystems will have flourished and disappeared. Humanity, as we know it, may no longer exist. But suppose that by some turn of fate, intelligent beings, whether descended from us, evolved anew from other species, or arriving as visitors from elsewhere, begin to study the ancient layers of Earth. What would they actually find of our world? They might first search for our monuments, the grand testaments to our ambition and ingenuity. Cities like New York, Tokyo, or Dubai, with their towers of steel and glass scraping the sky, seem so indestructible to us. Yet after only a few centuries without maintenance, they would collapse into rubble. After thousands of years, forests and deserts would reclaim them. After millions, the rubble would itself become part of the sedimentary record, buried layer by layer until only chemical hints of their construction materials remain. 100 million years later, not a single skyline would still stand. The Eiffel Tower, the Statue of Liberty, the Great Wall of China, even Mount Rushmore, all icons of culture and civilization, would be erased by weather, water, and plate tectonics. Maybe those future scientists would look instead to our infrastructure hidden in the ground: tunnels, pipelines, subway systems. For a time, some of these might survive, but eventually, they too would collapse, fill with sediment, and vanish into the Earth's ongoing recycling process. The very crust of the planet is in motion, swallowing old seafloor into the mantle while raising new mountains and coastlines. Our highways and subways, our mines and landfills, would not survive the endless conveyor belt of geology. So what would remain? Likely, only a thin and subtle layer in the geological record, perhaps only a few centimeters thick, marking the Anthropocene, the epoch shaped by human activity. That layer might contain unusual spikes of carbon isotopes, indicating our burning of fossil fuels. It might reveal higher than normal concentrations of nitrogen from our widespread use of fertilizers. It could show heavy metals like lead or mercury at levels inconsistent with natural processes. Tiny fragments of plastic, perhaps transformed under pressure into strange new minerals, might speckle the rocks. These would not look like discarded water bottles or grocery bags, but rather microscopic anomalies embedded in ancient sediments. Imagine a future geologist, 100 million years from now, analyzing those rocks under a microscope. They might notice an odd chemical fingerprint, an abrupt shift in carbon ratios, a brief scattering of synthetic molecules. They might see it as a blip, a small but intriguing deviation from the normal rhythms of Earth's chemistry. Would they recognize it as evidence of an industrial civilization? Or would they dismiss it as a natural fluctuation, like countless others in Earth's past? After all, they too would be subject to the same limits of imagination we face today. Without ruins or artifacts, without bones arranged in cities, how could they be certain that intelligence once thrived here? And perhaps that's the sobering point. Even if another civilization studied us in the far future, our presence might be reduced to little more than a puzzle piece, a faint whisper in the rocks. They might see the sudden warming event of our time and mistake it for a purely natural climate fluctuation, just as we wrestle with interpreting the causes of ancient events like the Paleocene-Eocene thermal maximum. They might never realize that billions of humans once walked the Earth, built machines that touched the stars, and transformed their planet in a blink of geological time. This perspective forces us to look at ourselves differently. We tend to believe our works are permanent, that our achievements will echo into eternity. Yet in the grand story of Earth, permanence is an illusion. To future scientists 100 million years away, our vast civilizations may appear not as ruins but as ghostly chemical shadows, fleeting evidence that intelligence once bloomed briefly before disappearing into silence. If we take this thought experiment and lift it beyond Earth, we stumble into a truly cosmic perspective. The challenge of detecting our own civilization in the far future becomes a mirror for understanding the challenge of detecting civilizations beyond our world. When we look up at the night sky, we see countless stars and, circling many of them, planets. Astronomers have already discovered thousands of exoplanets, and the list grows every year. Among them are rocky planets in habitable zones, places where liquid water might exist, and where, in theory, life could arise. The question that naturally follows is, if intelligent life has emerged elsewhere, would we be able to recognize it? Or could their civilizations have come and gone without leaving a trace detectable from across the stars? Think about how we search for alien civilizations today. We often look for signs of what scientists call technosignatures, observable evidence of advanced activity. This could be radio transmissions, powerful laser pulses, vast energy infrastructures, or planetary-scale engineering projects. Yet our ability to detect these things is limited. Radio signals disperse quickly over interstellar distances, fading into background noise. Even if a civilization broadcast across the galaxy, their signal would only be detectable for a finite time, and only if we were listening at the right moment, on the right frequency. The window of opportunity is small, and the universe is vast. Now consider the lesson from our own planet. If humanity disappeared tomorrow, within a few thousand years radio transmissions would cease. Satellites would fall from orbit, burning up in the atmosphere or crashing into Earth. In a few million years, almost all physical evidence of our existence would be erased. If an alien civilization scanned Earth from afar 100 million years in the future, they wouldn't see our cities, hear our broadcasts, or detect our satellites. They'd only see a planet with a strange layer of altered chemistry in its rocks, something completely invisible to telescopes. This suggests a humbling truth. Civilizations, no matter how advanced, may be nearly impossible to detect once they vanish. If we can barely imagine finding traces of a prior civilization on Earth, a planet we know intimately, What hope do we have of confidently identifying a long-gone civilization on a world light-years away? Even if alien life once flourished with technology, their evidence might be confined to geological strata, inaccessible to us. We could stare at their planet for centuries and see nothing but clouds, deserts, and oceans, unaware that deep beneath those surfaces lies the ghost of an entire civilization. The parallel is striking. Our inability to easily detect our own industrial footprint millions of years later reflects the near impossibility of recognizing alien civilizations across the stars. Both cases reveal the same truth, that intelligence is not guaranteed to leave obvious, lasting monuments. Instead, it leaves fragile traces, easily destroyed by time, erosion, and the relentless recycling of worlds. This raises profound questions for the search for extraterrestrial intelligence. When we point our telescopes outward, we often imagine civilizations like ours today, broadcasting, constructing, signaling their presence. But what if most civilizations, like us, are transient? What if the window in which they emit detectable signals is tiny compared to the lifetime of their planet or star? We could be scanning the cosmos at the wrong time, after countless civilizations have already risen and fallen. The silence we hear may not mean we are alone. It may simply mean that civilizations are fragile, and their traces fade quickly on cosmic scales. This connection between Earth's deep past and the search for alien life brings the Silurian hypothesis into sharper focus. If we want to understand how to detect industrial civilizations elsewhere, we first have to grapple with how we might, or might not, detect our own, millions of years into the future. The struggle to find ourselves is the same struggle we face in finding others. When scientists first put forward the Silurian hypothesis, they weren't secretly trying to smuggle in claims of ancient lost civilizations or suggest that reptilian humanoids once ruled the planet. Their goal was far more grounded, yet also far-reaching. The hypothesis was framed as a thought experiment, a way to sharpen our ability to recognize the traces of industrial activity across vast stretches of geological time. In other words, the question wasn't, did another civilization exist millions of years ago? But rather, if it had, what kind of evidence would it leave behind, and how could we distinguish that evidence from natural processes? That distinction matters deeply. Science thrives on testable questions, and the Silurian hypothesis opens a very practical line of inquiry. If we know how to identify subtle signals of industrialization on Earth's ancient record, then we also improve our ability to detect such signals on other planets. It becomes a training exercise, forcing us to think rigorously about what industry, technology, and civilization look like not just in the present, but after they've been buried beneath layers of time. Why would this matter? Because industrial activity leaves a planetary fingerprint. We see this happening with our own civilization right now. Carbon dioxide levels in the atmosphere have spiked because of fossil fuel burning, leaving a distinct isotope signature. Fertilizer use has altered nitrogen cycles worldwide. Plastics are embedding themselves into sediments, potentially forming future technofossils. Heavy metals from industry are concentrating in soils and waterways. And if nuclear technologies spread further, they too could leave unusual signatures in the rocks. Each of these is a possible technosignature, not just for aliens, but for us when viewed millions of years in the future. The Silurian hypothesis forces us to confront whether these signals would still be legible after immense spans of time. For instance, would plastic degrade beyond recognition, or could traces of microplastics persist? Would isotope anomalies smooth out through natural cycles, or would they endure as spikes in the rock record? By asking these questions, scientists are essentially stress-testing our ability to separate the natural from the artificial in Earth's history. And in doing so, they're preparing us for the much larger task of interpreting other worlds. It also has an unexpected application in climate science. By framing industrial activity as something that could leave long-term fingerprints, researchers gain another perspective on our current impact. If our industrial age were to end tomorrow, what parts of it would still be visible in the far future? The answer highlights the profound and lasting consequences of our activities. Even if humans vanish, our effects on climate and chemistry might linger in the rocks for millions of years. This doesn't just make us more careful scientists, it makes us more self-aware stewards of the planet. And here's something especially striking: the Silurian hypothesis underscores how hard it is to prove a negative. Just because we don't see obvious signs of a past civilization doesn't mean one absolutely never existed. Instead, it reminds us that the geological record is both incomplete and biased. Fossils are rare, surface features vanish, and plate tectonics constantly reshapes the crust. The absence of evidence is not the same as evidence of absence. By formally considering how an advanced civilization could disappear almost without a trace, scientists refine their understanding of the limits of detection. This is why the hypothesis is not fringe pseudoscience, but a serious, if playful, scientific exercise. It's not about indulging in conspiracy theories or suggesting Atlantis was real. It's about asking, how can we develop robust methods to tell apart natural geochemical changes from industrial ones? How can we recognize signs of intelligence when those signs are faint, fragmented, and embedded in the vastness of geological time? In this way, the Silurian hypothesis functions as a bridge. It connects paleontology, geology, climatology, and astrobiology into a single conversation. It humbles us with a reminder of how fragile civilizations' traces really are, while also equipping us with the intellectual tools to search for civilizations elsewhere. Scientists consider it not because they believe in hidden histories, but because they recognize how vital it is to train our eyes for subtlety in the rocks beneath our feet and in the stars above our heads. When we turn the Silurian hypothesis toward the field of climate science, its value becomes immediately clear. At first glance, it might sound like nothing more than a playful speculation about ancient civilizations, but in reality, it provides a powerful lens for looking at our present and our future. By asking what kind of industrial fingerprints might remain in the deep geological record, scientists can better understand the scale, permanence, and consequences of humanity's own activity on Earth today. One of the strongest connections between the hypothesis and climate science is the carbon cycle. When we burn fossil fuels, we aren't just releasing carbon dioxide, we're altering the very isotopic balance of carbon in the atmosphere and oceans. Fossil fuels are ancient carbon, locked away for hundreds of millions of years, and when released, they dilute the proportion of the heavier isotope carbon-13 compared to carbon-12. This leaves a distinct, measurable signature in the geological record. By studying past carbon isotope anomalies in ancient rocks and sediments, scientists can see whether sudden warming events, such as the Paleocene-Eocene thermal maximum, might look like our own industrial fingerprint. In effect, the hypothesis asks, could our civilization be mistaken, millions of years from now, for just another natural climate fluctuation? And conversely, could one of those past fluctuations have been industrial in origin without us recognizing it? For climate science, this is more than just a curiosity. It forces us to consider the scale of our impact relative to natural processes. If our emissions are creating changes in carbon ratios and global temperatures that rival some of the most dramatic climate shifts in Earth's history, then we can no longer think of ourselves as a small, transient influence. We are shaping the very fabric of Earth's long-term geochemical story. That recognition is sobering. Even if humanity ended tomorrow, our carbon signature could persist for tens of millions of years. It would become part of the geological library, a layer that future geologists, or perhaps even alien scientists, might one day study. Another implication for climate science lies in the study of feedback systems. The Silurian hypothesis makes us ask, if industrial civilizations existed before, what signs of their collapse would be visible? Did they push their climate systems past tipping points? Did they trigger extinctions, mass die-offs, or runaway warming? While we have no evidence that such a civilization existed, the act of asking those questions sharpens our ability to see how our own trajectory might unfold. It reminds us that industrialization is not just about immediate prosperity, it's about whether a species can adapt to the planetary consequences of its own activity. The hypothesis also highlights how fragile our markers truly are. Plastics, fertilizers, pesticides, and synthetic chemicals are spreading globally. They may form a detectable boundary in the rocks of the future. But over the span of tens of millions of years, even plastics may degrade, metals may corrode, and sediments may recycle. What endures most reliably is the change we are imposing on the climate system itself, the warming atmosphere, the acidifying oceans, the altered distribution of species. From the perspective of deep time, our climate legacy may be our loudest signature. And this is where the hypothesis folds back into practical climate science today. By framing our activities as geological events in the making, it strips away the illusion of human exceptionalism. We are not outside of Earth's processes. We are part of them, and our civilization is writing a chapter into the geological record whether we like it or not. It helps scientists communicate to the public that climate change is not merely about short-term weather patterns or regional disruptions. It is about leaving a permanent scar on Earth's timeline, a scar that will outlast cities, nations, and perhaps even species. In short, the Silurian hypothesis strengthens climate science by providing a framework to view our actions through the eyes of deep time. It says, if you want to understand the true consequences of industrial civilization, don't just look at the next decade or the next century. Ask what will be visible millions of years from now. And when you do, the scale of our impact becomes undeniable. Astrobiology is the science that seeks to answer one of the most profound questions humanity has ever asked. Are we alone in the universe? It is an interdisciplinary field, combining astronomy, biology, geology, chemistry, and planetary science to explore how life begins, evolves, and potentially spreads beyond its home planet. The Silurian hypothesis, while rooted in Earth's deep history, links directly into this field in a surprisingly practical way. It reminds us that if we can barely recognize the fingerprints of our own civilization in the deep past of our own planet, then the task of detecting civilizations across light years of distance becomes unimaginably more difficult. The key point is that civilizations leave behind fragile signals. When astrobiologists look for extraterrestrial life, they usually start with biosignatures, evidence of biological activity. This could mean oxygen in a planet's atmosphere, methane in the presence of oxygen, or patterns of gases that strongly suggest metabolism. But when it comes to technological civilizations, the search shifts to technosignatures. These could be radio signals, vast megastructures such as Dyson spheres, laser pulses, or planetary-scale chemical changes. Yet the Silurian hypothesis warns us, if these signals fade quickly on Earth, how much harder will they be to detect on other worlds, especially after millions of years? Take radio waves, for example. Humanity has been broadcasting for just over a century, a blink of an eye in cosmic terms. Our signals are already diffusing into space, blending into the background radiation of the galaxy. If another civilization sent out similar signals but collapsed before sustaining them for long, the odds of us detecting their broadcast at the right time and in the right frequency range would be vanishingly small. The window of detectability is short, and the galaxy is vast. Now think of chemical signatures. Our burning of fossil fuels is changing the carbon isotope ratios in the atmosphere. Our plastics are embedding themselves into sediments. Our fertilizers are altering nitrogen cycles. These are real, measurable technosignatures. But as the Silurian hypothesis highlights, over tens of millions of years, most of these will erode, degrade, or become indistinguishable from natural processes. If we cannot guarantee that future scientists on Earth will recognize our industrial age with certainty, then how confident can we be that we would notice similar changes on a distant exoplanet? This is not to say the search is hopeless. On the contrary, the hypothesis sharpens our thinking. It challenges astrobiologists to expand the range of technosignatures they consider, beyond flashy megastructures or clear radio beacons. Subtle signs, slight isotope anomalies, unusual atmospheric chemistry, strange thermal imbalances, might be just as important. But it also cultivates humility. Silence in our telescopes may not mean silence in the universe. Civilizations might bloom and vanish, their signals lost in the immensity of space and time. Here's another way the connection matters. Astrobiology often wrestles with the great filter problem, the question of why we don't see obvious signs of intelligent life despite the staggering number of stars and planets. The Silurian hypothesis provides a sobering clue. Perhaps civilizations are not rare, but their detectable traces are fleeting. They may alter their planets, just as we are altering ours, but those alterations get buried, erased, or reabsorbed by geological and atmospheric processes. This would mean the silence we hear is not proof of absence, but proof of fragility. By linking our deep time perspective to the cosmic search, the Silurian hypothesis turns Earth into a kind of test case. It says, before you go scanning the stars for civilizations, try finding your own. If it's hard here, it will be even harder out there. This forces astrobiology to refine its methods, to look for subtle and ambiguous clues, and to accept that certainty may remain elusive. And yet, there's also something profoundly inspiring in this. The act of searching binds us into a larger story. Whether or not other civilizations exist, the very fact that we wonder about them shows our place in the cosmos. The Silurian hypothesis doesn't close doors, it opens them. It reminds us that the universe may be filled with hidden histories, and that our own story is just one thread in an incomprehensibly vast tapestry. About 56 million years ago, long before humans, long before even our earliest primate ancestors had taken their tentative steps, Earth underwent one of the most dramatic climate events in its history. The Paleocene-Eocene thermal maximum, or PTM. This event has become a focal point in discussions about the Silurian hypothesis because it mirrors, in uncanny ways, the kind of planetary changes that industrial civilizations, ours included, are capable of producing. When scientists look back at this episode, they see a world transformed almost overnight by a mysterious surge of carbon into the atmosphere and oceans, triggering massive warming, ocean acidification, and sweeping ecological upheavals. And here's the unsettling thought: if geologists were to study our era millions of years from now, they might mistake our fingerprints for something very much like the PTM. Or, more provocatively, if another civilization had existed back then, could their industrial activity have been responsible? The PTM is marked by a sharp spike in global temperatures, with average surface temperatures rising by as much as 5 to 8 degrees Celsius over just a few thousand years, a blink of an eye in geological terms. The oceans warmed, polar ice all but vanished, and lush, subtropical forests expanded far into regions that today are temperate. Horses, primates, and other mammals diversified rapidly during this time, suggesting that the climate shift opened ecological niches. But the event was not all opportunity. Many deep-sea organisms, particularly benthic foraminifera, suffered severe die-offs due to the sudden acidification of ocean waters. The crisis reshaped ecosystems on a planetary scale. What made this event stand out to scientists studying the Silurian hypothesis is the signature it left in the carbon cycle. Geological records show a significant drop in the ratio of carbon-13 to carbon-12 isotopes during the PTM. This kind of anomaly is precisely what happens when massive amounts of carbon, derived from ancient organic sources like fossil fuels, are released into the atmosphere. In our own time, the burning of oil, coal, and natural gas is leaving exactly this isotopic fingerprint. The eerie similarity raises the question: what exactly caused the PTM's carbon surge? The mainstream scientific explanations focus on natural sources. One leading theory points to the destabilization of methane hydrates, frozen deposits of methane trapped under ocean sediments. A warming trigger, perhaps volcanic activity or orbital changes, could have released vast amounts of methane, which later oxidized into carbon dioxide, amplifying greenhouse effects. Another theory involves massive volcanic outpourings associated with the North Atlantic igneous province, which would have pumped greenhouse gases into the atmosphere. Yet, for all these explanations, the PTM remains somewhat mysterious. The sheer speed and scale of the carbon release don't fit neatly into any single natural mechanism. This is where the Silurian hypothesis edges into the conversation, not to claim that the PTM was definitely caused by an ancient civilization, but to highlight how difficult it is to disentangle natural and industrial fingerprints across deep time. If we look at our own fossil fuel combustion, we see almost exactly the same isotope shifts, the same global warming, the same ecological disruptions. If geologists millions of years in the future were trying to interpret our era, they would face the same ambiguities. Without direct artifacts, without concrete traces of technology, how could they be certain whether the anomaly was natural or artificial? And if the PTM were industrial in origin, would we have any way to tell today? The implications are unsettling but also illuminating. On one hand, they remind us how easily our own activities could be lost in the sands of time. On the other, they serve as a cautionary mirror. The PTM lasted around 200,000 years before the Earth system stabilized. Imagine the scale of suffering, extinctions, and transformations locked into that stretch of time. If we are, through our industrial activity, recreating a PTM-like event today, then we are not simply warming the planet temporarily. We are initiating a geologic scale disruption that could take hundreds of thousands of years to fully heal. This connection underscores the practical value of the Silurian hypothesis. By entertaining the possibility of past civilizations, we sharpen our tools for detecting the fingerprints of industrial activity. The PETM becomes a natural laboratory, a test case for asking, if we want to distinguish between natural climate shifts and industrial ones, what evidence would we need? What signals would be unambiguous? And right now, looking at our own emissions, what are we leaving behind that could survive as a clear marker millions of years in the future? In the end, most scientists lean toward natural causes for the PETM, and rightly so. Occam's razor suggests that methane release or volcanic activity is far more likely than a vanished civilization. But the beauty of the Silurian hypothesis is that it forces us to hold the mirror up to ourselves. If an ancient geologist had examined Earth during the PETM, they might have wondered, could life itself have engineered this? And if we now see ourselves engineering similar changes, then the PETM becomes less of a mystery and more of a warning, a reminder that planetary systems are sensitive, and once pushed out of balance, they can spiral into states that last far beyond the lifetime of any species. Roughly 2 billion years ago, long before multicellular life had even begun to diversify on Earth, something extraordinary happened in what is now Gabon, West Africa. Deep in the crust, inside deposits of rich uranium ore, natural conditions aligned so perfectly that the rocks themselves became self-sustaining nuclear reactors. These natural fission zones, discovered at a site called Oklo in the 1970s, shocked the scientific world. Until then, the idea of a nuclear reactor was synonymous with human technology, with industrial ingenuity, with engineering mastery. But here was proof that nature itself, given the right circumstances, could run a nuclear chain reaction and keep it going for hundreds of thousands of years. The story of Oklo begins with uranium, an element that exists in multiple isotopes. The isotope uranium-235 is the one that sustains nuclear fission, the chain reaction that splits atoms and releases massive amounts of energy. Today, uranium ore contains only about 0.7% uranium-235. But 2 billion years ago, due to the slow decay of radioactive isotopes, that percentage was higher, around 3%. And here's the twist. 3% is about the same concentration that modern nuclear power plants use once their uranium is enriched. In other words, nature's uranium at the time was already fuel grade. Now imagine groundwater seeping through the uranium-rich rocks. Water acted as a moderator, slowing down neutrons released during fission and allowing the chain reaction to sustain itself. The process cycled on and off like a natural heartbeat. When the rocks got too hot, the water boiled away, stopping the reaction. Once things cooled down, the water returned and the cycle started again. This continued for hundreds of thousands of years across multiple reactor zones, releasing immense energy on a planetary scale, all without a single human hand involved. Why does this matter to the Silurian hypothesis? Because it demonstrates just how easily nature can mimic what we normally consider technological signatures. If a geologist millions of years in the future stumbled across remnants of Oklo without knowing about natural fission, they might be tempted to interpret it as evidence of a technological civilization harnessing nuclear power. The isotopic ratios left behind in the ore, the depletion of uranium-235, and the presence of certain fission byproducts look almost identical to what you would find in the waste from a human-built reactor. Yet in this case, no intelligence was involved at all, just the blind mechanics of geology, chemistry, and physics. This is a sobering reminder when we think about detecting lost civilizations in deep time. If nature itself can create something as striking as a nuclear reactor, then how many other signatures we associate with technology might also arise without any civilization at all? A massive release of carbon could point to industrial activity, or to methane hydrates destabilizing. Heavy metal anomalies in the rock record might suggest mining, but could equally result from volcanism. Traces of nuclear activity might whisper of vanished reactors, but as Gabon proves, they can also be purely natural. The Earth is full of complex processes that, from the perspective of deep time, can imitate the work of intelligent beings. At the same time, the Oklo discovery is inspiring. It shows that the universe is far more creative and surprising than we often give it credit for. The boundary between natural and artificial is not as clear as we might think when looking back across billions of years. For scientists considering the Silurian hypothesis, Oklo stands as both a caution and a guide. It cautions us not to leap to conclusions when we encounter unusual signals in the rock record, because nature has its own ways of producing anomalies. And it guides us toward humility, reminding us that the traces of a true civilization, if one ever existed before us, would have to be separated very carefully from the countless imitations the Earth itself produces. In this way, Oklo helps refine the scientific method. It forces us to ask, what counts as undeniable evidence of technology? If uranium deposits can behave like reactors without civilization, then what other signals might trick us into thinking intelligence was at work? And by extension, how can we be sure when searching not just Earth's past, but also the surfaces of Mars, Venus, or exoplanets light years away, that what we are seeing is truly technological and not simply the artistry of nature? The natural reactors of Gabon show us that the Earth has always been capable of surprises. They are, in a sense, a geological riddle posed across time. If we misinterpret them, we could be fooled into imagining civilizations where none existed. If we understand them, we sharpen our ability to distinguish natural processes from real techno-signatures. And that is exactly the skill the Silurian Hypothesis demands of us, an awareness that the Earth's history is full of both mysteries and mirages, and that the line between them is far more delicate than we often realize. And so we circle back to the question that has been quietly humming in the background of every idea we've explored so far. If another civilization lived here millions of years ago, would we even know? After all the discussions of erosion, plate tectonics, the rarity of fossils, the degradability of plastics and metals, the misleading imitations created by natural processes like the PETM or the natural nuclear reactors of Gabon, after weighing all of that, what does it actually mean for our ability to recognize a truly ancient civilization if one ever existed? At first glance, it feels like the answer should be obvious. Surely skyscrapers, power plants, highways, or spacecraft would leave undeniable ruins that even after millions of years would be recognizable as artifacts. But once we step back and take a geological perspective, the certainty begins to crumble. Think about it. We live in a world that is constantly reshaping itself. Continents drift across the planet, mountains rise and erode, seas open and close, and entire landscapes vanish under layers of sediment. In only a few tens of millions of years, entire ocean floors are recycled back into the mantle. Against such relentless processes, even the strongest human monuments would stand little chance. The Great Wall of China, the pyramids of Giza, the tallest skyscrapers in New York or Dubai, give them a few million years, and not only would they be unrecognizable, they would most likely be erased completely. This is why the central question isn't just a piece of science fiction. It's a scientific puzzle of enormous depth. Our own existence today, with all its technological marvels, could easily disappear from the record given enough time. If we vanished tomorrow, and a new species evolved 100 million years from now, would they be able to tell we were ever here? And if the answer is maybe not, then how could we expect to uncover the traces of a civilization that might have lived and died not just millions, but tens or hundreds of millions of years ago? It forces us to confront the fragility of evidence. Human history feels vast to us, thousands of years of written records, monuments, and artifacts. But in geological time, it's a flicker, less than a single frame in a movie that's been running for billions of years. And so, the real challenge is not whether a civilization could have existed in deep time, but whether anything of it could possibly remain for us to find. The uncomfortable answer is that even if such a civilization had thrived, even if it had spanned the globe, its traces could be so thoroughly erased by Earth's natural processes that the story would be forever lost to us. But there's another layer to this. The question is not only about physical remnants but about interpretation. Suppose we do stumble across anomalies, strange isotopic ratios, unusual patterns in fossil gaps, odd concentrations of metals or chemicals in ancient sediments. Would we even be able to interpret them as evidence of civilization? Or would we, bound by Occam's razor and the weight of natural explanations, dismiss them as volcanic events, asteroid impacts, or simple quirks of the carbon cycle? In other words, could the evidence be hiding in plain sight, but rendered invisible by our assumptions? This tension, between what might be and what we can actually prove, is what makes the Silurian hypothesis so fascinating. It isn't claiming that a forgotten civilization did exist. It's asking a much sharper, and in some ways, a more unsettling question. If one had existed, could we ever know? And the answer seems to be that our ability to know is far less certain than we would like to think. The Earth is an old planet. It has seen countless ages rise and fall, climates shift, oceans advance and retreat, life forms bloom and vanish. To assume that intelligence, industrial, technological intelligence, could only have appeared once in all that time may be more of a bias rooted in human exceptionalism than in evidence. But even if it had appeared before, we may never find proof. The silence of the geological record does not necessarily mean absence, it might just mean erasure. And so, the central question lingers in a kind of uneasy balance. Perhaps we are the first and only civilization Earth has ever known. Or perhaps we are not the first, only the first to leave faint echoes that future beings might interpret. The unsettling truth is that we may never know for certain, because time is both a preserver and a destroyer. It buries as much as it records, and in that silence lies the possibility that entire chapters of Earth's history have been lost to us forever. When we allow ourselves to step back from the comfort of what we know and instead open the door to what might be, the imagination begins to paint extraordinary possibilities. Earth stops being just the planet we inherited and starts becoming a vast canvas, layered with stories that may never have been told. Think about the world beneath your feet, not just the soil, not just the bedrock, but the countless layers of time stacked upon one another, each holding fragments of an age long gone. Some of those fragments are familiar to us: the bones of dinosaurs, the shells of ancient sea creatures, the pollen of long-extinct plants. But what about the gaps? The missing pieces? Could those blank stretches of the record hold more than just the silence of nature? Could they conceal whispers of civilizations that rose, thrived, and vanished before we were even a possibility? Inviting this kind of imagination is not about abandoning science. It's about stretching the mind far enough to appreciate the scale of the unknown. Our textbooks present Earth's history in neat chapters: the Precambrian, the Paleozoic, the Mesozoic, the Cenozoic. But real history is not written in straight lines or tidy narratives. It is chaotic, uneven, and full of mysteries. For billions of years, life on Earth has been experimenting, failing, adapting, and transforming. Why should intelligence be a one-time event? Why not an experiment repeated, perhaps in a different form, perhaps in a different age, with outcomes we can only imagine? Picture walking through a forest today, the sunlight slanting through the leaves, birdsong in the air, and beneath your feet roots pushing through ancient soils. Now imagine that same place 100 million years ago. Perhaps a city once stood there, not of humans, but of another kind of being, maybe reptilian, insectoid, or something entirely alien to our biology. Their towers may have been built not of glass and steel but of materials we wouldn't even recognize as artificial, things that time has long since broken down into dust indistinguishable from natural rock. That forest today could be standing on top of a forgotten metropolis, the past and present woven together without a trace to the untrained eye. It's humbling to consider Earth as a place of hidden histories. We're taught to think of ourselves as the pinnacle, as the first and only to achieve technology, culture, and society. But perhaps we're only the latest layer in a much deeper story. Perhaps civilizations are not permanent, but temporary flashes, brief experiments in intelligence that flare up, transform the world for a moment, and then vanish into geological silence. Encouraging imagination doesn't mean replacing science with fantasy. It means recognizing that the scientific record is not complete, that what we see is only a fraction of what once was. It means giving ourselves permission to think of Earth not only as our planet, but as a world with a vast, mysterious past that may hold surprises beyond anything we expect. Maybe we'll never uncover direct evidence of another civilization, but the act of imagining opens us up to new ways of thinking about ourselves. It teaches us humility. It shows us that our story may not be the only story this planet has hosted. And in the end, imagination is often the first step toward discovery. By daring to ask, what if? We prepare ourselves to recognize evidence we might otherwise overlook. By wondering if Earth has hidden histories, we train our eyes to see beyond the obvious and our minds to accept that the universe is stranger, richer, and far more mysterious than our narrow slice of time suggests. As fascinating as all of this speculation may be, we need to pause and plant our feet firmly back on the ground of science. The Silurian Hypothesis, for all its intrigue and all the imaginative doors it opens, is not evidence that a lost civilization actually existed on Earth millions of years ago. It is not a discovery, nor is it a claim of proof. Instead, it's an intellectual exercise, a way for scientists to test the limits of what we could detect if such a civilization had ever risen and fallen in the distant past. That distinction is crucial. The human mind loves mystery, and it also loves to connect dots, even when the connections are not there. When we hear about strange anomalies in the fossil record, about sudden extinctions or unexplained warming events, our instincts lean towards searching for meaning, for intent, for some hidden hand at play. But science works differently. Science thrives on evidence, testable predictions, and explanations that can withstand scrutiny. And when we look at the evidence so far, there is nothing, no artifacts, no unambiguous traces, no ruins, that would support the idea of an advanced civilization before ours. The Silurian hypothesis exists to sharpen our tools of detection, not to rewrite history. It asks, what signatures does our civilization leave behind? How long will they last? And if we were to vanish, what would geologists 100 million years in the future be able to see of us? By running through these questions, scientists are better able to think critically about Earth's deep past, and also about the search for life beyond our world. But the key is that it remains a thought experiment. This grounding is essential, because without it, the conversation drifts into the realm of pseudoscience and unfounded speculation. The world is full of claims about lost civilizations, Atlantis, ancient aliens, hidden empires buried under ice or sea. Those stories capture the imagination, but they rarely engage with geology, paleontology, or the hard realities of how evidence survives across deep time. The Silurian hypothesis is different. It does not say, here is proof of a lost race of beings. It says, let's pretend there was one, how would we even know? And in doing so, it provides a framework rooted in science, not fantasy. This doesn't make the idea any less fascinating. If anything, it makes it more powerful. Because it forces us to balance imagination with skepticism, to stretch our thinking while never letting go of the anchor of evidence. It reminds us that science is not just about knowing, it's also about asking better questions. By grounding the conversation, the Silurian hypothesis protects us from drifting too far into myth while still giving us space to wonder about the mysteries hidden in the vastness of Earth's history. So as we continue, keep in mind this critical point: there is no evidence of a forgotten advanced civilization. None. But by treating the idea seriously as a thought experiment, scientists gain insight into geology, into climate science, into the resilience, or fragility, of our own civilization, and even into how we might recognize intelligence elsewhere in the universe. The strength of the hypothesis is not that it proves another species once built cities and machines, but that it teaches us how to look, how to question, and how to understand the traces we ourselves are leaving behind. And so, after walking through all the science, the speculation, the immense stretches of time, and the fragile nature of evidence, we return to the heart of the mystery, the haunting question that began this journey. If another civilization had once risen on Earth, millions of years before our own, would we even know it? The honest answer, after everything we've explored, is that we probably wouldn't. The Earth erases, recycles, and transforms itself with such relentless power that almost nothing endures beyond a few million years. What survives are fragments, fossils, chemical traces, rare geological scars, and even those are extraordinarily incomplete. This realization is both humbling and unsettling. On one hand, it strips away some of the arrogance we tend to carry when we see ourselves as the pinnacle of creation, the inevitable outcome of evolution. On the other hand, it leaves open a vast field of possibility. If civilizations are so easily lost to time, then the absence of evidence is not necessarily evidence of absence. We could be the very first to build a technological society on this world, or we could be one among several, our chapter following others long since buried beneath stone and sea. And when you stop to think about it, this perspective reshapes how we view ourselves in the present. We like to imagine our skyscrapers, satellites, and global reach as indelible marks of progress. But to the Earth, we are a brief flicker. Our industrial age has barely lasted 2 centuries. If we last another 10,000 years, it will still be an instant compared to the deep time of geology. And if we vanish, if our cities crumble and our machines dissolve into dust, then in a few million years almost nothing will remain. A geologist of the far future, whether human or something entirely different, might sift through layers of rock and find only a faint anomaly, a brief disturbance in chemistry, a trace so subtle it could just as easily be mistaken for a natural fluctuation. It's a sobering thought. Everything we are, everything we've built, could vanish so completely that the Earth forgets us. But it's also a reminder that the story of Earth is bigger than us. Bigger than our cities, our nations, our species. The Silurian Hypothesis invites us to imagine Earth not as a stage built solely for humanity, but as an ancient, ever-changing world that may have hosted more stories than we will ever know. And so, we close with a reflection, a line that lingers in the air like an echo from deep time itself. Perhaps we are the first. Or perhaps we are only the latest chapter in Earth's long, forgotten story. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.